Okay, I'll start then. So hello everyone. So welcome to this tutorial. My name is Xiaohong Chen. So I'm a PhD student at the University of Illinois at Urbana-Champaign. And I work with my supervisor, Professor Gregory Rasu, on programming and language design, program logics, and verification. So in this tutorial, I'll introduce you the K language framework. I will show you how to define your own programming languages using the K framework in an easy and fun way. As I said, if you want to get the materials that we'll be using in this tutorial, please go to my homepage. I've put the web link there. I'll show you more details about how you can get K after. I'll put up the slides on my homepage after this tutorial as well. If you have any questions, please ask at any time during the talk, or you can send me an email after the talk. I'm very happy to answer your questions. So let me start with an overview of the tutorial. I'll first
Please paste the link to the homepage in the chat.
No, so I think you have to, right, I don't think it's clippable on your side. You have to type it in a URL, or you can search my name.
Yeah, can you paste it into the chat?
I think it's the chat for the Zoom is not turned on for this session.
Oh, it's disabled. Yeah, I was trying to do it myself, but it seems to be disabled.
Right, disabled. So I think what I can do is to go to the Clouder and post a link there. Yeah, I think an easy way is to actually to type my name and the university name, and you'll find my homepage. So I think that's the easy way. Just type in name and University of Illinois at Urbana-Champaign, you'll find my homepage there.
It's very strange that we don't have a chat. That would have been so useful.
Yeah, I don't know why it is disabled. All right, so let's let me start with an overview then.
Sorry, I just have one question. You said this was going to be recorded. Where is the recording going to be?
I think it will be uploaded to ACM website.
Thank you.
Yeah.
Are you recording it yourself, or you are asked by the organizers to push the record button, Xiaohong?
So it is optional, and I actually filled a form, the release form, to the organizers.
Okay. But they are responsible for posting it, not you.
Yes.
Right?
Yes.
Okay.
Yeah.
I believe there's also a tutorials 1 chat on Clouder. You could post the link there.
Okay, but I don't think I've access to Clouder right now.
I can put it there.
Yeah, all right. Yeah, that would be helpful. Thank you.
Sorry, could I just take a screenshot of the URL?
Sure.
Okay, thank you. I'll put it in the chat.
Thank you. Okay, so the overview of the tutorial is I'll first give the vision of an ideal language semantic framework. I'll briefly discuss what is the current status quo of programming language design and what's wrong with it in our view, and how we can improve it by this ideal vision. Then I'll show you an overview of the K semantic framework. So K can be regarded as our attempt towards the vision of the ideal framework. I'll show you the history of the K framework and its current application in programming language design and formal analysis. Then we get into the core part of this tutorial, which is to learn how to use the K framework to design our own programming languages. We'll start from the basics and define a simple higher order functional language, which we call Lambda. Once we define the formal syntax and semantics, we'll use K to automatically generate a parser and an interpreter for Lambda, which will allow us to actually execute Lambda programs. That is to say, the K semantics that we define is an executable and testable formal semantics. Then apart from the parsers and interpreters, K can generate many other language tools, such as deductive verifiers and bounded model checkers. So in this tutorial, I will not discuss those tools in detail, but I will give you some references at the end of the talk. So if you are interested, feel free to check it out. And then I would use K to define a rather complex language, which we call fun. So fun is also a high order functional language where functions are first-class values, but it also has many other interesting features such as inductive data types and pattern matching. So it's much more like the real-world functional languages such as OCaml. So in this tutorial, we'll define the complete executable K semantics for fun. We want to show you that it is 100% practical to use only formal methods to design a programming language that is not a toy language, but a real language that people actually can use in practice. And finally, I will discuss how type checkers and type inferencers can be defined in K as well. We'll define several type systems and end up with defining the famous Hindley-Milner let polymorphic type inferencer in K. So that's the overview of this tutorial. Before we start, let me say that I will give you lots of demos during the tutorial, and it's best if you can get a copy of K and try the demos by yourself. So if you do not have K installed, the easy ways would be to get to this VM image, which can be accessed on my homepage. I think this is probably the simplest way, so I highly recommend it. An alternative is to use the K online interface, which has an older version of K running on the web service that you can try. But I have not tested the demos on this older online interface, so it might fail on some tests. Also, if you use the online interface, please wait for the process to terminate, or if you want to quit at runtime, please kill the process manually so we won't have too many processes running on the machine at the same time. You can also compile K from source. This is quite simple, but will take some time, 30 to 60 minutes for K to compile, so I don't recommend doing it now. And also, please be interactive, so ask questions at any time. Please ask, just unmute your microphone so I know you have a question, I will answer it right away. So any questions? All right, so now let's start with the first item, which is the vision of an ideal language semantic framework. So we often use this picture to illustrate the ideal framework. So in the center, the yellow part represents the formal definition of any programming language, including its syntax and semantics. Then the framework will automatically generate all the language tools from the formal definition for that language. And these tools include the basic execution tools such as parsers, interpreters, compilers, to formal analysis tools such as the deductive program verifiers and model checkers. So the main objective of this ideal vision is to make programming language design simple, easy, rigorous, fun, and following a well-principled way. What is to notice here is that the real job, which is to define the formal semantics, is done by human once and for all. So all the rest is done automatically by the framework. Because in theory, once we have the formal definition, the framework has everything it needs to generate all the language tools. So if our language has a newer version, all we need to do is to just update the formal definition to the newer version, and the framework will take care of the rest and generate new tools for us. In other words, these tools are correct by construction. There is nothing to be argued about the correctness of these tools in the sense that they are always generated directly from the formal semantics. There's no such modeling gap between the formal model of the language and the language implementations themselves. So we firmly believe in this ideal framework vision, and we think that it's even possible to have an intuitive and attractive notation for the framework. So it is also accessible to, so Randall?
Yeah, just an idea. You mentioned going from one version of your language to another, and I guess you could perhaps automatically generate migrations, if you know what I mean.
Oh, you mean the translation from an old version to a newer version?
Yeah.
Yeah, but I don't think we have that currently in K, but that's definitely doable. So it'll be a translation on the semantics.
Yeah.
Yeah. Okay, so yeah, thanks for the question. Guri, do you have anything to say about that before I continue?
I think that would be an interesting tool. That would kind of be outside this picture, right? It would be something that takes a language definition and some characteristics, some description of how we want to evolve that language into a newer version of the language, right? And then generate a new version of the language. But then the rest of the tools would take a new language definition as input. So they are not incremental, right? So they are not, actually the interpreter is sort of incremental in the sense that the LLVM backend allows you to link modules together, right? So, I mean, you may have a language where you only modify one semantic module, but keep the others unchanged, right? Then in principle, you can generate the tool a bit faster. But the time to generate a tool is never so critical that, I mean, that was not the weak part ever, right, you know, of the approach. But yeah, it would be nice to have DSLs or high-level description meta languages describe how a language evolves from one version to another. And in general, it would be nice to have ways to define abstractions and translations of some sort from one semantics to another. Like even a type system for a language, in some sense, it would be nice to derive it automatically based on some high-level principles, you know, or you describe what kind of type system you want, and then you get another definition automatically. That would be nice, but we haven't done these things yet.
And that would be one level above K.
Yeah. I mean, what is here on this picture is already hard enough.
Yeah. So yeah, thanks for the comments. So yeah, I was talking that, you know, we apart from this picture, we also want to have a very intuitive and attractive front-end notation for the yellow formal language definition. And the point of that is the users, you know, the formal definition is also accessible to non-experts. So we'll make formal methods and formal tools more popular and more easy to use and easy to understand. And at the same time, everything we do here is still mathematically rigorous. So this is, of course, a very long-standing dream of the programming language and formal verification communities. And our objective with the K framework is to develop the foundations, techniques, and tools to make this dream a reality. So before I dive into how we approach the ideal language framework vision with K, so let me start with a few words about the status quo. And unfortunately, the state of the art is still far from the ideal vision. So the programming language and formal methods communities still develop each language tool individually for each programming language. Compilers are perhaps the most known language-specific tools, like we have GCC and Clang for C, but there are many, many other tools besides compilers that are being developed specifically for each language. For example, there are also interpreters for C that target at detecting undefined behavior, like the trust in soft interpreter. Then we have model checkers for C, like CBMC. Then we have symbolic execution and program verifiers for C, like the Microsoft VCC. Many of these tools are developed essentially from scratch, sharing very little code or functionality with each other. And when the C language evolves, for example, from C11 to C17, all the tools need to be updated. And then
2017, in the small Rust Belt town of Lebanon, Ohio, 8 Republicans and 8 Democrats, despite all their fear and apprehension.
Okay. Sorry, was that a comment or a question? Okay, I'll keep going. So So basically the same story unfolds for other popular languages like for Java or JavaScript and among others. And now we can see the same thing happening over and over again with the emerging blockchain languages such as the Ethereum VM bytecode. So in short, this is the story of the current status of programming language design. And it created a maintenance hell. So if you have L languages and T tools, then we need to develop and maintain at least L times T systems. Not to mention all the talent wasted in doing the same or similar thing, the same tools implementing the same fundamental algorithms and abstractions, but for different languages. So we think that this situation is at best uneconomical. So how it should be, as I said, we need an ideal language framework to do all the tool generating work. And for our intelligent programming language designer, we should not waste our time in implementing language tools. We should define the formal semantics of each language and let the ideal framework take care of the rest. So this is the ideal vision, which is also our vision of language semantic framework that we push with K. So let me get into the second part, which is the overview of the K framework. So the K framework is our attempt to—
can't write anything on that page, which makes me wonder why the space is even there in the first place. Under the app settings, you can manage your files. You can clear some files, which just means clearing the list, not actually deleting.
Sorry, was that a question on the talk?
No, I think somebody may have unmuted by mistake.
Okay, okay.
So yes. Don't worry.
My apologies.
Yeah, okay. So so let me start with the K framework. So this is the homepage to the K framework, so feel free to check it out. So in short, K is a 20-year continuous effort towards the ideal framework. And in that process, we have learned a lot from many existing formal semantic styles and approaches. So we learned from small step semantics, big step semantics, evaluation context, abstract machines, and there are many variants of them, chemical abstract machines, axiomatic semantics, continuation, denotational, and initial algebra semantics. So we found that each of these semantic styles has its own limitations. So the main thing is that they work very well on small languages, but break apart very quickly when we attempt to define large languages such as C and Java, especially in terms of the basic engineering aspects that mathematicians tend to disregard, such as modularity and heavy use of notation, or in terms of serving more than one purposes, for example, incapability to do formal verification of some of the languages. So the development of K was based on these understandings about the existing semantic styles. And initially, K was engineered to keep the advantages and avoid the limitations of various semantic styles. It incorporated all the features we encountered in the various semantic approaches that appear to work well when defining real languages like C and Java, and we avoided all the features that were inconvenient or demotivating for large languages. For example, in many semantic approaches, one has to modify or duplicate many unrelated semantic rules when we add a new feature to the existing language. For example, when adding side effects to a language or a new internal stack for exception, for example, or input and output or concurrency, etc. So such break of modularity or need for duplication in the semantics are simply unacceptable in practice. So in K, we engineered mechanisms and notations to avoid those duplications. Then, once several large languages were formalized across various language paradigms, and there were no significant requests from users for new features or changes to the K itself, we decided to develop the mathematical details of the K's underlying theory. And the result is a very simple and beautiful theoretical foundation, which we call the matching logic, that works as the practical foundation for a complex and feature-rich framework like K. So if you're interested in the theory of K, you can look up the matching logic at this website, so matchinglogic.org. So let me give you a very high-level introduction to how you define things in K by means of a simple example language. So here is a complete K definition of kernel C, which is a fragment of C. The left column defines its formal syntax, and the other two columns define its formal semantics. I'll next zoom through this definition and highlight some of the K2's features. So the syntax is declared using the conventional BNF notation, annotated with the K attributes, so the blue part. For example, the assignment statement is an expression construct taking two expression arguments. The left one can be a variable or a pointer, for example, star x, etc. So we only discuss the formal case here. So let's say that the first argument is a variable. The strict of two annotation states that the assignment is strict in the second argument. That is, that argument needs to be evaluated first. So the semantic rule of assignment, which we discussed shortly, then can assume that the second argument is already a value. So this is the way that we define syntax in K using the conventional BNF notation. So one important concept in K is called computation configurations. So K makes heavy use of configurations, which in the tool can be defined and initialized in a user-friendly and colorful way. A configuration can be regarded as a snapshot of the program execution. So it includes the remaining program, the computation. It also includes all the necessary semantic information that we need to execute the program. So K configurations are organized as nested cell structures whose leaves hold basic data organized in lists, maps, sets, etc. And a cell can be referred to by its name, and the order of cells is irrelevant. For example, in kernel C, the K cell here will hold the remaining code or the computation, the program that needs to be executed. And the funcs, which holds the set of functions, the env cell holds the current environment, and for the current heap, the function stack, input buffers and output buffers, and also the malloc free pointer map, and so on. And once we have the syntax and configuration, we can start adding semantic rules. So K rules are contextual. They mention a configuration context in which they apply. And also they mention the local changes that they make to that context. For example, so here we have the semantic rule for the assignment. So remember that assignment was strict of two. So we can assume that the second argument is a value, say V. The context of this rule involves two cells, the K cell and the env cell. And there are two notations. So in the above, we show this graphical way, and below we show this ANSI style. So when we develop a language, we write things in this ANSI style. And there's an automatic tool to generate these graphical styles because it just looks nicer. So for each cell, we only need to mention the pieces of information that we actually need for the semantics. So from the K cell, we only need to know the first task, which is the assignment. And from the environment cell, we only need to know the binding, X binds to what, and not the rest. So this underscore here, it is an anonymous variable. So the intuition here is the value will be discarded anyway after the assignment, so there's no need to bother naming it. The unnecessary part of the cells, which we call structural frames, are completely ignored here and automatically inferred by K. So this is suggested by the tiers in the graphical notation or the ... in the ANSI notation. So ... means things that, the computation frames which are there, but they don't care and they do not change after the rewriting. So once the local context is established, so we identify the parts of the context which needs to change and underline them, and then provide the changes under the lines or after the rewrite symbol, which is equal, greater than symbol. We call it rewrite symbol in ANSI style. So in our case here, we rewrite both the assignment to the value of X, and also we rewrite the value of X in the environment to the assigned value V. So everything else stays unchanged. So we don't mention them. We just represent them using the ... notation. And the concurrent semantics of K regards each rule like this as a transaction on the configuration. So all changes in a rule happen concurrently. Moreover, rules themselves apply concurrently, provided their changes do not overlap. So this is essentially how K definitions look like. And we hope that this makes sense and it's not too difficult to understand. So before we continue, do we have any questions here?
Yes.
Yes, please.
Yes.
Yes, go ahead. I heard that there is a question.
I have a question. I was trying to find how to raise the hand. I think there was somebody else. I thought it was somebody else where the question was. It was not me who thought. I was not the one talking. So my question is very simple. It's about kind of like terminology. You use this word configuration, and the more you're talking, I'm thinking, oh, that's what I normally call the state of the computation, the entire machine, the entire state.
Yes, yes.
That'd be okay? All right.
Yeah, that's okay. That's okay. So we use this big word configuration because states are heavily overloaded in the programming language design. So sometimes it refers to just mapping from variables, from locations to the values in a memory. So we use the word configuration, but that is the entire state of the computation. Yes.
I fully agree with you. The word is very overloaded, but I just wanted to know if I had the right mental image of this.
Yeah, yeah, you're right.
Okay. Question?
If
yes,
I remember, oh, sorry, John, you go ahead.
Okay, thanks. So in a given program run, is there only one configuration or can there be many configurations?
There's only one configuration, but you can have as many cells as you like in one configuration.
So the concurrency is sort of manifested through the evolving state of the various cells. Is that right?
Yes.
Okay.
Yes.
All right, thanks.
You can have one cell per thread, and each cell can have its own code, its own continuation, its own environment, and rules match and apply concurrently.
Okay, thanks.
So
yes, I did have just to clarify my understanding of this, that with cells, they are what you just are limited to things you describe as basically algebraic data types. Is that, I guess, one way to think about it, or initial algebras or whatever. Is that correct or incorrect?
They don't have to be initial algebras, but yes, we axiomatize all the properties that we need axiomatically, equationally, and using algebraic data type philosophy. But we do not require initial algebra or initial model semantics.
Okay.
All right. Yeah. Thank you for the questions.
And also the terminology, we didn't invent it. It's also the terminology used in other operational semantics frameworks. In SOS, where you have these tuples, they also called configurations. So you need some data structure, indeed, in which you can store everything, a snapshot of the system, of the program at any given moment. And it can be arbitrarily complex, arbitrarily nested. Yes, and concurrent as well.
Right. So K-scales. So we've tried smaller and toy languages, but there are also some large and real languages that have been given semantics in K. As previously explained, K itself has been designed and developed while defining the semantics of these languages. So we have the JavaScript semantics. So it not only passed all the conformance tests proposed by the standard committee, but it also found weaknesses in it and confirmed bugs in all major browsers. And then we have the Java semantics, which resulted in the most semantic complete test suite for Java, and almost 10,000 small programs that cover all the semantic rules are generated as a consequence of defining semantics for Java. So x86 semantics defines the semantics of more than 3,000 x86 instructions and variants, and it is the only complete x86 semantics to date. The C semantics is by far the most complex K semantics. It is the complete semantics of K, and it covers all the language features, including all the undefined behaviors. And recently, we looked at the semantics of blockchain languages, such as the low-level Ethereum VM bytecode, Solidity, Wasm, Viper, Yale, and so on. And all these language semantics have been thoroughly tested on large benchmarks of programs, just like how other compilers and interpreters are doing. And many other large K semantics are under development at this point. So the conclusion here is that K scales and is practical. All right, so that's enough about the ideal vision and the big picture of K. So let's dive into K and start by defining a very simple functional language called Lambda in K. Later, we'll extend it by one tricky language feature, which is callcc, call with the current continuation, to show that it is very easy to modify and extend the existing languages in K. It is well known that functional languages can be given a formal semantics based on substitution, or given a formal semantics based on environment or closures. So K is neutral here, and we can support both styles in K. And in this tutorial, we'll do both. We'll do the substitution-based semantics first, and then we extend the feature callcc where we shift to the environment-based style. So we can see both styles here in K. So defining Lambda. As said, Lambda is a very simple functional language. We'll define it using a substitution-based style. What I'm showing here is the general workflow to define a programming language in K. So first, we start by writing down some example programs in our language. And then we define the formal syntax. And then we define the computation configurations of our language, and record that a configuration holds all the semantic information that is needed to execute the programs. So, and finally, we define the formal semantics. So this is the basic workflow to defining any programming languages in K. And we'll also follow this workflow in this tutorial. So let's first write some example programs of Lambda and their intended evaluation results. And note that we are the language designer here. So we decide what our language should look like and what language features it should have. So, so here I give 3 example programs. So you can see that we are using quite standard functional language syntax here. So the language has letrec to define recursive functions. It also has an explicit mule construct to build fixed points. So both letrec and mule can be used to define recursions. Let us look at the first program. It is a factorial function. So it calculates the factorial of 10. So the intended result will be this number. So the second program, so we have a mule of Lambda and then an if then else statement applied to 7. So if you look carefully, this is the so this behavior is, if x is less than 1, then x itself. Otherwise, it's f of x minus 1 plus f of x minus 2. So this defines the Fibonacci function. So f of 7 should be 13. And then we have the last program. So it's just a very simple lambda calculus expression. And by applying the beta reduction rule, we know the result is y, right? Because by applying this rule, you will end up with lambda, by variable renaming, have lambda z dot y, and apply to z, you'll have y. So ay is the result. So the point of this program is to test the alpha renaming and capture avoiding substitution. So if we apply beta reduction without alpha renaming, we'll get lambda y dot y. So now y is captured, and then apply to z, so which equals to z. So this test program makes sure that we have the intended capture avoiding substitution correctly implemented in the semantics. So these are the three examples programs of Lambda. Okay, so now let's define the syntax of it. So on the left, we show the entire syntax definition. So let's read it from the beginning. Require substitution.md asks K to load the predefined substitution module because we are going, we have followed a substitution-based style here. So in that module, the capture avoiding substitution is already implemented, so we can simply reuse it in our definition here. And then the module Lambda starts the definition of Lambda. It first imports the predefined module domains for domain values such as integers and booleans, and also the substitution module from the capture, for the capture avoiding substitution that we'll be using in this semantics. Then we have the syntax definition, where we use the conventional BNF notation to define non-terminals such as vals and exp. And val is the non-terminal, or we call it a sort for Lambda values. A value is either a variable or a Lambda abstraction. So the predefined sort kvar is the variable sort that the built-in substitution module knows. So it knows how to generate free variables for that sort. So we just reuse it. And we can see that the terminals are quoted as strings. And the binder attribute specifies that the Lambda abstraction is a binder. So the substitution module knows how to provide the capture avoiding substitution for Lambda. Now we define exp as either a value or an application, and also we use the parentheses for grouping. So the left attribute for application says that it is left associative, and this information will be only used for parsing. The strict attribute, which we have seen before, defines evaluation context. It states that application is strict in both arguments. So they will be fully evaluated to values before we evaluate the application. The bracket attribute tells K that parentheses are only used for grouping. So K will not add it to the internal abstract syntax trees. And we do not need to bother giving parentheses a form of semantics. So they will just only use for parsing purpose. Then the rest of the syntax is pretty clear. So we use integers and booleans. So we define them as values here. We also define arithmetic operations and multiplication, division, addition, and the comparison between two integers. And some of them are associative, but some are not. So you can see the attribute here. But all of them are strict in their arguments. Also note that we use the arrow here instead of a bar to mean that the formal construct, so multiplication and division, have a higher priority than the letter construct, which is also expected. We also define if and else. So note that if and else is strict of 1 because we only want the first argument of if and else to be evaluated, which is the condition, and not the second and the third argument. Then we define letrec, and mu, where mu is also a binder, just like Lambda. And finally, we define the K result. So since we have the strictness attribute to ask K fully evaluate an expression to the final result, we need to tell K what are considered as the final results. And the built-in sort k result is for this purpose. So we define all the values to be evaluation results. So that's it for the syntax. Now we can ask K to automatically generate a parser for Lambda, which will parse well-formed programs into ASTs, and it will reject EU-formed programs. So I can show you my first demo here.
Can you explain why the let and letrec are not annotated with binder?
Yeah, that's a good question, because in the semantics, we'll be defining them by desugaring them to Lambda and mu. So the binding behavior will be obtained there. So we don't need to define them as binders, but we can. You're right, we can define them as binders, but they will be just syntactic sugar for Lambda and mu. So the binding behavior will be inherited from Lambda and mu. Does that answer your question?
Yes, thank you.
Okay, yeah, thank you. So that's a good question. And yeah, let me show you the demo one. So if you already have the demo files, you will see several folders for the demo. And what? Sorry, can you all see my screen here?
Yes, we can see the screen.
Okay, so let me just get into.
The font is a bit small. If you can increase it a bit, that would be good, but not.
Yeah, I can. So I'll try bigger. Does it look good?
Better.
Okay. Okay, let me make this bigger as well. 20. Okay. Great. All right. So let me go to the demos. If you download demo files, you will find these demos. If you go to it, so we have the demos. Let me go to the demo one, which is for Lambda. And you see there's a lambda.k file. Let me also open the README. So we have a lambda.k, and if you look at it, this is essentially the definition that we just saw on the slides. So this is the k definition. And the first thing we need to do is to compile this. So k will generate all the language tools for us. To compile it, we use the command kcompile.
But it's important to clarify that this is an incomplete definition, right? You don't have yet the beta reduction.
Right,
or
right.
the sugarings of letrec.
That's right. That's
so now any program that you have, it will be just a term, basically, unsparsed.
So for now, we only have the syntax.
Okay.
Yeah, we don't have a semantic. This is just a syntax. But this is from the syntax,
definition of the syntax, right?
Sorry, what?
This is a full definition of the syntax.
Yes, that's right. Yes.
Yeah. Okay.
So we can generate a full parser for Lambda already. So let me show you how to do it. There are many backends. I will be using the Java backend, which is going to be outdated, but it's quite stable. So I'll just use it for this demo. And we'll give the lambda k and let k compile it.
So by the way, I think the last line is cut from the terminal. If you can make the terminal a bit smaller.
Yeah, I'll fix
it. At the bottom.
Okay, this should be good now.
Yeah.
And also let me
May I ask a quick question?
Yes.
In the syntax, there is a rule for the lambda and a rule for the mu.
Yes.
And I'm thinking the difference is one corresponds to the non-terminal val and the other to x. But those are essentially the same thing, aren't they? It's just the lambda abstraction, right? Or so otherwise, I don't know. Maybe I don't know what mu really means, but the mu rule and the lambda rule on the right-hand side are identical. And they seem to me like lambda abstractions. So, and that will create a conflict with the rule that says that a value is an expression.
They are not identical, right? Because we're defining the syntax here, and they have they are different syntax. We have the.
Yeah, I understand. They're mu there, so that they will not be confused. But aren't they redundant for the language?
No, because mu is the fixed point. So
okay, thank you.
Yeah, yeah, and it will be clear when we see the
I was
semantic.
wondering what's the difference.
Yeah. So lambda is just a normal lambda function closure, but mu is the fixed point closure.
So apologize for my ignorance. Thank you.
Okay, so yeah, so now we have the definition compiled. So the warning basically says that it expects a syntax module, but because this language is so simple, we only have one module for everything, so we can just ignore it. All right, so now what we can do is to parse some programs. So let me just show you some example programs. So let's say the Fibonacci program, which looks like this. We saw it before. So what we can do is we can use cast.
Actually, this shows that mu is a fixed point.
Yeah, right.
Because you say mu, the fixed point in f, that function that takes x and does the magic of Fibonacci.
Yeah, thank you.
Right, so we can.
But again, we don't have the semantics yet, so this is just a term at this stage, right? So K has no idea that mu is a fixed point or lambda is lambda.
No, it's just in our head right now. It's not in K.
Yeah.
So KST, cast stands for the KAST. It's essentially a parser. So we can give the cast this program. And what it does is we parse this according to the formal syntax and give this big term. So it looks terrible, but it's quite, so yeah, it's just an AST format for K. And what we can do is let's make some stupid syntax error. So for example, I just forget to add the parentheses around mu. And the problem with that is now we can have a parsing ambiguity because we don't know whether it is the mu applied to 7 or mu, whether the 7 is inside mu or not, right? So there's a parsing ambiguity. So we can confirm this ambiguity by calling cast. And K will say that, okay, there is a parsing ambiguity. And the nice thing is it will show you in this cast format. So it's easier for debugging, all right? So that's just a very simple demo showing you how to generate language tools from K. So let's get back to the slides. Oops. Any questions? Okay. So yeah, so we just saw the demo one.
Yes, I had one high-level question.
Yep.
And later on in your demo or in your story, you're getting into the type system. Suppose I wanted to prove some meta results about, say, a type inference algorithm. That it say is sound or infers principal types. What sort of mechanization support is there for that? Okay.
So K has a prover, so it allows you to prove reachability properties. If I start from this configuration, I can end up with some properties like that. So if there's a way to express your properties, meta properties about the type system as such reachability rules. So if I start from this program, I end up with that type, then K can prove it automatically. If it requires more,
not always, it may need lemmas and so on, but it has support for that.
Yes. Yeah.
Mm-hmm.
Okay. Thanks.
But if the properties are more complex, like if you want to relate two different semantics, like concrete dynamic semantics and the static semantics for a type system, then then K, as it is now, doesn't give you support for that. We used to have, and I'm not sure if it has been updated, a callc backend to K, which allows you to take these definitions in K and generate callc definitions, and then you can use callc to do those proofs interactively or semi-automatically.
Okay, thanks.
Mm-hmm.
Sorry, I was looking away at the moment that you showed what. So you run K compile, and then you get a parser. How do you run the parser on a test program?
I use the cast command.
KAST, that's the parser.
KAST, yes, that's a parser. So what happens is once we compiled the definition, you'll see there's a folder called lambda-k compiled. So that includes all the language tools. And by calling cast in this at here on the program, it will just call the parsers of Lambda to parse the programs.
Okay,
yeah,
I'll try that.
Okay. So yeah, that's a demo one. So let's get into the semantics. So in K, formal semantics is defined using rewrite rules. So a rewrite rule has the form left-hand side rewrites to right-hand side, and it has a natural expected meaning. So if the current program configuration matches the left-hand side of a rule, that rule can be applied, and K will rewrite the match part into the right-hand side. So for example, let us take a look at this rule for if and else. So it says that if my current program code is if true, then E, else underscore, then it should rewrite to E, so which is the then branch. So if the current code is if false, then underscore else E, then it rewrites to E. So these two rules together give a complete definition of the if then else statement. And the reason that it is complete is because in the syntax part, if you still remember, we define if then else to be strict of 1, which means that it is strict in the first argument. So here we can assume that the first argument has already been fully evaluated to a value, and thus it is a value either true or false, the Boolean values. So we only need to consider two cases, whether it's true or it's false. Let's look at the first rule, which defines beta reduction. So note that on the right-hand side, we are calling the predefined capture avoiding substitution construct to substitute V for X. And after renaming is handled internally by K, by the predefined substitution module. So we don't need to do anything special about it here, except that in the syntax definition, we mark Lambda as a binder using the K attribute. So this is pretty straightforward definition of Lambda, of beta reduction in K as a rewrite rule. And then the next 4 rules defines the semantics of arithmetic operations. They rewrite the programming language constructs to the corresponding integer operations, which are predefined in K as well. So note that K allows you to write conditional rules. For division, for example, we require that I2 must not be 0. So if I2 equals to 0, there's no semantic rule that can be applied. So K will just get stuck during the execution. Let's now look at the last 3 rules here, which are the most interesting ones. So the let rule defines let as a syntactic sugar for lambda x dot e prime applied to E. And we use the macro attribute to say that this is a syntactic sugar. So the desugaring will be carried out as soon as the program is parsed and before the actual semantic rules are applied. So similarly, letrec will be desugared to let using mu, and then let will be desugared to lambda and function application, and so on. So the last rule defines the formal semantics of mu by unfolding itself. So mu xe rewrites to E, which is the body of the fixed point, but will replace every occurrence of the binding variable x by the mu expression itself. So in other words, to evaluate a fixed point, we evaluate its body, where the binding variable x in the body is replaced by the fixed point itself. So that's it for all the semantics. So we close the module definition by the keyword and module. And now we have a complete K definition of lambda, including both the syntax and the semantics. So now K can generate for us an interpreter that can execute lambda programs. So we are going to show you the second demo. Randall, yes?
Yes, sorry, it might already be obvious, but do the rules have to be written in that sequence? For example, letrec needs to be written after let because it uses let, or can they be shuffled?
They can be any order. So it's essentially a set of rules. So rules have no order between each other.
Cool, thanks.
Mm-hmm. All right, so let me show you the second demo, which is to show you how, so now we have the complete Lambda definition. We can execute Lambda programs. So let me open the README on the right, so you can see what I'm going to do. And on the left, we have lambda.k, but this time, as you can see, it is complete. So it has everything here. And let's compile it. So actually, I already pre-compiled all the definitions, but let's still compile it for now. So if you are doing the demos on your own machine, you will have to compile every language definitions in the demos. But I have them compiled here. So in the future, I may just skip the compile part to save some time. Okay, so let's see the program's Fibonacci again. So this is the program. And to call the execution, we'll use the command called krun. So that's the interpreter that K generates for the language. So we can call krun on the Fibonacci. It'll take some time to parse the program, and the result is 13, right? So you see that K, we haven't defined configuration for Lambda, but K, if there is no configuration, K just puts it in a K cell, which is the current computation. So the result is 13, as expected. We can do more programs. So let's see some division by 0. Right? So what happens if I have a division by 0? So note that we are doing integer division here. So 2 divided by 3 will be 0, the integer 0. So we'll have 1 divided by 0 here. Okay. So if we ask K to run this program, what will happen is we'll get stuck at this point because the semantics of division requires, the second argument to be non-zero. So if it is 0, it will just get stuck here. All right. So let's.
I'd like to make a comment before you continue, Xiaohong.
Yes.
So you mentioned, but you mentioned it in passing that K has several backends. So this is the Java backend, which is the legacy backend, is the most complete one, but also one of the slowest. So
yeah,
the parser in particular is slow. So that's why all this is. It looks like it is so slow. A lot of the time is spent with the parser. There is a backend which is super fast, comparatively at least, the LLVM backend, but that is not as general as this one. So that's why Xiaohong prefer to choose the Java backend.
Yes. So because I want to show you the substitution-based definition.
Right. Also, if you want to use K and performance is bothering you, let us know, because there are ways to improve the performance even with the Java backend. Are you using the K server now? You're not using the K server, I guess.
I'm not using the K server. It's just running on my local machine.
So there are mechanisms to make this faster, but performance was not the topic of this presentation. So that's why I didn't focus on performance.
That's a good comment. Thanks. So let me go back to this Fibonacci because it's defined using mu. So it's interesting how K handles mu. So what I'm going to do is we can ask K to execute the program step by step. So I can give it an option called dep, and K will just execute the programs by the given number of steps. So if I give it 0, it will be just a program itself without executing. Let me give it 1. So what happens if K will just execute it by 1 step, and you see that what happens is so this is an application. So mu applied to 7, and remember that application is strict. So both arguments have to be a value, right? So now the 7 is a value, but not mu. So what K will do is it will start to evaluate mu, and that's what it is all about. So it put mu as the first computation task. followed by 7. So now K focus on evaluating mu. And once it evaluates mu to a value, it will come back and apply that value to 7. So that's what happens. And if we can
so the execution model underneath under the hood is based on abstract machines. There's like an abstract machine here that converted the program into a sequence of tasks.
Yes, yes. And the sequence of tasks is linked by this squiggy arrow notation. So now you can see that we can execute for 2 steps, and K will unfold this mu to the body, right? So lambda x, if x. So that's the body of the mu. But the variable of f has been replaced by mu itself. And that's where the recursion comes in. And now we have a lambda, and lambda is a value, if you remember. So now we have a lambda applied to 7, and that will trigger the beta reduction and so on. So I hope this gives you an idea. I won't do all the demos here because that will take us a lot of time, but I think all of you have a good idea about how K execute programs. So that's demo 2. Any questions for demo 2? Okay. So to conclude, so this picture illustrates what we just saw with K. So on the left, we have the K formal semantics of lambda saved in the file lambda.k. And then we can use the kcompile command to compile the K definition. And that results in a set of language tools specific to the language lambda. So we have used a parser and the interpreter, but there are many tools like the verifiers and boundary model checkers in this blue bubble. To use the interpreter, we call the command krun, which takes the compiled K definition and a lambda program, for example, factorial, and executes the program following the formal semantics. And when the execution finishes, it returns the result. What is to note here is that only the formal semantics is finished by human. So this part is done by human. And all programming language tools in this blue bubble are generated by K fully automatically. All right, so that finished the first part, defining the semantics of lambda. Now, let us extend lambda to lambda++. With one more language feature, the callcc, which is the call with the current continuation. And this time we'll shift to an environment-based definition, just to show you that K supports both the substitution style and environment or the closure styles easily. And after lambda++, we can have a short break, I think, where I can take some more questions. So let's follow the K workflow again, and first write down some programs for lambda++. So I give 3 programs here, so all of which are about the callcc construct that we'll be adding to lambda. So intuitively, callcc is the construct that takes a function as its argument, and the semantics of callcc is to apply that function on the on the current continuation or the current computation. For example, let's look at the first example. We have let here, and then a callcc. So, so by the semantics of let, the program means that callcc lambda k, and then we have +1 here. And according to the semantics of callcc, what will happen is that this function lambda k dot let x equals 2 in k of x, this function will be applied to the current continuation. So note that I've underscored the scope of the callcc. So the continuation of this callcc expression is something +1, right? Because the value of x is 1 by the let construct. And let's remember that. So the continuation is something +1. Then by evaluating the callcc, we apply the function, this inner lambda function, to the current continuation, which is something +1. And that results in evaluating the body of this function, which is let x equals 2 in k of x. And when the continuation k becomes something plus 1, we have 2 plus 1, right? Because x is 2 in this context. And therefore, the result is 3. So that's essentially how KCC works. It takes a function, and it applies that function on the current context, computation context you are in. So let's look at a second example here. One thing to note here is that the semantics of let that we define is by desugaring to lambda and application. So essentially, we are given a lazy semantics here because we do not first evaluate the values that we bind to the variables that in the let expressions, and therefore we end up with it's simply an expression, a plus b, where a becomes this callcc expression, and b becomes 1, right? And then we get to the first example and the result is 3. So if you see clearly, the first example exactly, this callcc expression plus 1, right? So the result is 3. So this program can be used to test whether let is given a lazy or an eager semantics. The last program just shows that the inner let will shadow the outer let. We simply needed to identify what is the continuation when callcc is called. So in this case, when callcc is called, the context is something times 10 plus x, right? So what is x? It is the inner x2. So the context is something plus 10, something times 10 plus 2. And the continuation is applied to the value 3 here. So we have 3 times 10 plus 2. So the result is 32. So these are just the examples of callcc. It is a very tricky language, but it's also a very powerful language. So from callcc, you can define, for example, the try-catch block and many other interesting language constructs. Yes,
sorry, I didn't
questions? Yes.
So why is callcc needed in the syntax? Like it looks like you could write that with just the let x equals 1 in taking the first program, let x equals 1 in that lambda, etc., and you get the same result. Like if this was
you mean why do we need callcc in our language?
Yeah, like it seems to me like if you left it out, you'd get the same behavior. I don't really understand why it's needed.
You mean if we cross callcc from here?
If you remove
I don't think you get the same result, right? Because what callcc does, it takes a function and it applies the function on the entire configuration that you have. So it will take a snapshot of all the configuration you are currently doing. So you are in the middle of doing something, right? And when you see a callcc, you will wrap up all the job you're doing right now, and you forget about it, and you jump into callcc and do what callcc asks you to do, which is totally something different. And by this k, the continuation parameter, there's always a chance for you to get back to your original job, right? So I think that's a very powerful construct. You cannot achieve it by,
But I think the point here is that these examples are pretty simple, and callcc is not really super important for these kind of examples, right? So callcc is an amazing construct in general, right? In languages like Scheme and other functional languages, but these examples here, they are pretty simple, right? It's not like they illustrate the power of callcc.
Right. So in later of the talk, you will see how we can define try-catch block, so exception using callcc just by desugaring to callcc. So does that answer the questions or?
Yeah. So basically, it's coming soon. Yeah.
Yeah. It's coming. Yeah.
The interesting part is coming soon.
Yeah. So okay. So now let's define the syntax. So we'll be using an environment-based style. So we don't need to import the substitution module anymore. And we don't need the binder attribute because it'll be handled by the environment and the closures and all that. So in an environment-based definition, Lambda abstraction will be evaluated to the function closures. So Lambda is not regarded as a value anymore. Apart from that, the syntax is the same, right? So in the end of the definition, we add a callcc construct, which is stricting the argument, but that's it. We don't need to change the syntax. In practice, it's a good habit to divide the semantics of our programming languages into smaller modules. So usually there is a syntax module and a semantic module. So here we put all the syntax definition here in the syntax module. And as usual with this syntax module, K can give us a parser of Lambda++, as in the language Lambda case. Now, let's follow the K workflow and define the program configurations for Lambda++. So configuration is a very important concept in K. It includes all the semantic information needed to execute the programs. For example, in C, if we want to execute this program, we need to know the value of n. Or to execute this program, we need to know the status of the threads T1 and T2. And in summary, this semantic information will be stored in configuration. And defining configurations is usually the first step towards the formal semantics, because at this point, we'll start to think about the semantic information that we need in order to execute the program. So for Lambda, we need only a simple configuration. In K, configurations are defined like this. So we just saw that, organized in cells. And each cell has a name, and it holds a particular type of the semantic information. And in general, configuration cells can be nested. The Lambda++ configuration consists of 3 cells. So let me just close the window. Give me a minute. Yeah, sorry about the noise. All right, so we have the K cell, which holds the program, or we call the computation. And the program we denoted by the special variable called $PGM. So this is the program that we give it to K run to execute. So K will parse the program and put it here in the K cell as the initial configuration. And then we have the environment cell, which is a mapping from variables to locations, and the store cell, which is a mapping from locations to values. So initially, both maps are empty. So in the configuration, we define them using .map. In K, dot means nothing. So initially, we have no maps at all. They're empty maps. So we write .map to mean the type of the nothing is map. So which are the empty maps. And we can make cells colorful. So that's mainly, they're easier to read in a terminal. So that's the configuration definition. It's pretty simple. So just the computation cells plus 2 cells for variables. Okay. So now we have the syntax and the configuration. We can define the semantics of Lambda++. And you will notice that the first difference from the substitution-based semantics is that we define the function closure as the value here of evaluating a Lambda abstraction. So a closure holds an environment, which is a mapping from variables to locations, and a variable name, which is the name of the parameter of the function, and an expression, so which is the body of the function. When we see a Lambda in the computation, we will write it into this closure value. And when we apply this closure to a value, so that's the second rule here, we'll evaluate the body of the closure in the environment where the parameter x is reallocated to a fresh variable n. So this ban n notation is how we generate a fresh value for the type. So we'll give the parameter x a new fresh location in the environment cell, and in the store cell, we'll bind that new location to the value v. And in that new environment, we evaluate the body of the closure, right? So, and once the evaluation finishes, we need to restore the environment row prime, which we discussed shortly after. So there are two tests here. So when we want to apply a function closure to a value, we first evaluate the body in that closure in a new environment that we create for the parameter. And after that, when the evaluation finishes, we need to get back to the original environment, which is rho prime. And so note that in the store cell, we rewrite the dot map to this new binding. And this is the typical way how we add new things to a mapping by matching on the empty map and rewrite that to something else. So this band-end notation asks K to generate a fresh value. So we use it to generate a fresh location. And this tutor, this squiggy arrow notation, we've seen it before. So it is a built-in construct for computation composition. And in K, computation is like this sequence of tasks. And these tasks are composed using this squiggy arrow notation. There's no difference on how K matches over this squiggy arrow in the K cell and how it matches the other user-defined language constructs. So whenever we see a value followed by an environment, we know that this is the result of applying a closure to a value. And what we need to do is to restore the environment and keep going, right? So this is what the fourth rule is all about here. The fourth rule is all about. So whenever we see a value followed by environment, we know it is a result of a function application. So what we are going to do is to restore the environment. So the rule above is the variable lookup rule. It looks at the value of a variable x by first looking at the environment cell and finds the location n, and then look up a value v associated to n in the store cell, and then it rewrites x to v, okay? Then the arithmetic operation semantics is the same as in Lambda, so we omit them here. So what's different is how we evaluate fixed point. So just like Lambda, mu also has its own closures. The mu closure consists of the environment map and the fixed point body. So map and the body. But this time we don't need a parameter variable. And the reason for that is can be found in the following rule. So let's see the following rule here. So to evaluate mu xe, we do not touch the environment. We'll just simply allocate a new location here. We'll allocate a new location for the entire mu closure, right? And in the closure, we update the environment by mapping x, which is the binding variable, to that new fresh location. So in other words, in evaluating mu, the variable x is already registered in the environment and it is assigned to the mu closure itself. So when we evaluate the mu closure, we only need to unfold and evaluate the body in the given environment. And then the evaluation finishes, we store the original environment. So that's the semantics of mu. And you can see how recursion occurs here because when creating the closure, we immediately assign x a new location, even if we assign x a location where the location stores itself, right? So that's where the recursion comes in. And finally, let's look at a rule for callcc. And recall that callcc is all about continuation. So for lambda++, continuation can be represented as a computation plus the environment in which the computation takes place. So again, we define a closure for callcc. So in this time, we call it cc, taking an environment and a computation. So K represents computation. Whenever callcc is called on a value, with the rest computation being K, and the environment being rho, we rewrite the callcc into an application where we apply the value v on the callcc closure. So v applied to the callcc closure with the computation k and the environment rho. So this is like taking a snapshot of the current continuation in this closure, and we apply the value v on that closure. And note that we also leave the current computation K here and we don't touch it. So if the callcc doesn't trigger the continuation, we'll finish the evaluation and comes back to K, which is the original computation, and keep going, right? If we indeed trigger the continuation, we are going to drop the remaining computation and rewrite the entire K cell into V followed by K, right? So in other words, we restore the computation K with value V under the environment row, right? So there are two cases here. Either we trigger the continuation or we don't. If we do trigger the continuation, we follow the continuation, we'll forget whatever the original computation is. Now, do we have any questions about this semantics? Any questions?
Hi, just a quick question. How do you, just wondering how you kind of test this? How do you test that it's what you intended it to be, or for more complex?
So how do we what?
Like if you wanted to be sure that your semantics was what you intended it to be,
how do we test it?
What's the process for testing that it is indeed, you didn't make any mistakes, etc.?
Yeah, so remember we have this workflow. So we write lots of example programs and their intended behaviors. And we use those programs to test our semantics because this semantics is executable. So we can ask K to run those example programs with this semantics and see if the results are expected. If not, we know we make a mistake. So it's pretty much like a test-driven methodology here in K. Yeah, Randall?
Cool, thanks.
Yeah, thanks for the question.
Sorry, for real languages like C or Java or JavaScript, we start by collecting lots and lots of tests. Basically, we take benchmarks that compiler or interpreter developers use to test their implementations and develop the semantics by running those tests, seeing where the semantics gets stuck, understanding why it got stuck, fixing the problem or adding more semantics, and so on and so forth until we pass all the tests. Is the resulting semantics correct? We don't know. The way I like to tell students in class is that a semantics is a definition of a language, a semantic definition of a language is correct by definition, right? Because that's what you mean. Whether it's the intended language or not, you don't know. You just have to test. And at some moment you can also run the tests symbolically, so you can have like symbolic tests, and those give you more confidence. K also has the search capability where you can search for non-deterministic state space of behaviors, and if you see unexpected behaviors, then you can find bugs in the semantics. So, but in general, you keep finding bugs in semantics. We have a semantics of C11 where we formally define the ISO C11 standard. And we keep so we started in 2012, right? And even now, and that's part of a product in runtime verification in a company. And even now, after all these years, we keep finding bugs in the semantics, things that we misunderstood, things that surface when we run tricky programs, so it's a continuous development process, semantics, which is why we have developed this firm belief that you need executable semantics, because if your semantics is not executable, then how do you trust it? How do you have confidence in it? Of course, it's nice to prove a semantics sound or two semantics equivalent, but that's very hard in general. So we'd rather, the K philosophy is that you have only one semantics and generate various tools from it. And the various tools help you find various types of bugs that you may not find with other semantics or other tools. But very, very good question. Yes, how to know if a semantics is correct? Testing.
Yeah. I remember there's one more question.
Yeah, that's me.
Yeah.
I must be honest, I'm not fully getting my head around exactly what callcc and mu are doing, but my question is just, it's probably okay just to continue with the tutorial without actually really understanding that, or is it important to really understand that right now?
I think it's okay to, so the point we were showing here is that these are very tricky language constructs, and if you just, if you first encounter them, it's very hard to understand them. But in K, you can define it in 3 lines. So I think that's a point. So for very complex, and it's not something that we come up with. So callcc is something that's very popular, and it's known to be a very tricky language construct. And many other semantic styles, I would say, will have a big problem in defining semantic for callcc, but not in K. So you can see that the semantics for callcc in K is quite short, but it does tricky things. As you see, you either to remember the current snapshot of a system, and if you see the callcc, we need to restore it. So yes, it is complex. But for the tutorial, I think it's okay. If you don't understand it now, I think it's okay to move on.
Okay. Cool,
if you want to, it's a very tricky construct. But if you want to read about it, you can search for callcc scheme. I think scheme is the language that explains it best. It's a core construct in scheme.
Mm-hmm.
Intuitively, it's like you capture the current context in which you are and wrap it up as a value and put it in your pocket. Okay, and you continue the execution, and then you can take it from there whenever you want, and you can go back in time to where you were. The way I like to teach it to students is in terms of games, because students play games all the time, and it's like playing a game, and then it's late and you want to save the game, right, and continue tomorrow, or send it to your friend to continue, right? So you just save the game. So you save the context, and that thing that you saved, the file, now you can send by email as an attachment to somebody else, and somebody else can continue exactly from that point whenever they want to. So same with callcc. You can execute the program, you reach a certain point, you say, oh, I really like this place in the program execution, this context. Grab it, keep it. And then later on, you can jump back into the exact same context by passing a value to that continuation, current continuation value. It's super cool. Do you have examples? Do you have exceptions with callcc?
I have. It will come in when we define fun. So do we have exception there?
Yeah. So with callcc, you can define exceptions. You can define abrupt termination in functions, abrupt return. You can define lots of crazy things. Even recursion, right? I think if you have side effects, you can even have recursion and iteration with callcc. It's super powerful, but also very complex to define. I think in standard SOS, the small step operational semantics, you cannot really define it, right? Because in small step SOS, not reduction semantics with evaluation context, but just standard SOS, the program context is in the proof context. That you derive a proof, and you are part of that proof. During the execution, and you cannot just grab the proof and store it in your store, right? But if you have evaluation context, then you can, because you can match the evaluation context in which you are, and that's the value that callcc evaluates to.
Okay. Yeah, thanks for the comment. Yeah, please.
Can you explain what the structural annotation means?
Oh, right, yes. So it just tells K to not count this as a computation step. So remember that when we run K run, we can ask K to run for a given number of steps. If any rule is targeted as a structural, that would be not counted towards that bound. But in terms of execution, it has no effect. So okay, we just execute the programs, apply these rules as usual. It's not considered as a computation step. It's just a the structure step. Changing the configuration from one structure to another equivalent structure.
Thank you.
All right, so I'm going to show you the third demo, and then we can have a short break. I think it's yeah. So let me show you the third demo. Also, let me open the README on the right. And note that this is a different environment-based style. So we can, if we run the Fibonacci program, which is the same program that we saw this program in the substitution-based definition. But now if you run it in the environment-based definition, we end up with this big configuration. The value is also 13, but in the store, we have lots of pointers. And this is partly because we are not doing garbage collection in the semantics. But still, you can see that we get the right result. So let me just run one program, the callcc program. So remember that this is the callcc program. And if we run it, so actually I don't need to run it because I have the results on the right screen, so you can see it if you trust me. So if you run it, we can have the result 3. And you will see that somewhere in the store, we have this CC closure, which is like the game save file that Gregory mentioned. This is a snapshot of your current configuration. Like you save the game and this has become save of a file. And you can restore the game whenever you want in the computation. And so I want to show you this. So if you use the depth option to run this step by step, you'll see how the semantic rules are applied one by one, and how K unfolds the closure and apply the CC closure to the values and restore the environment and all that. Okay. All right. So just before we take a break, let me discuss briefly how what makes K scale to large languages like C and Java. So one important feature in my view is the high extensibility and the modularity, which is obtained by loosely coupling of language features. So for example, this is the variable lookup rule that we define in Lambda++. And note that how we only mention the parts that are absolutely needed for the semantics, but do not duplicate anything. And this is crucial. As a language designer, any duplication made in the formal semantics will be eventually backfire and hurt ourselves. So K really put that to the extreme and tolerates no duplication. So what makes it possible is the front-end interface that we see here, which allows us to mention only things that are needed and use this ... notation that we've seen before for the computation frames. If we don't have this, we need to write rules like this, right? We need to mention all the cells, and not only all the cells, but everything inside a cell, right? So we need to mention the environment, the store, even if they are frames, they don't change. So, so basically everything in green here on the right-hand side are duplicate information, so except the V, right? That's something new, but everything else you duplicate it. So if we define our semantics like this, then every time we need to update the language, for example, adding a new cell for IO or for exception, we need to come back to this rule and make changes here, and this makes it not scalable. And using the above notation, we make sure that the language features are loosely coupled in a formal definition. So no matter how the language changes, this lookup rule is the same, right? As long as we don't change how environment and store are represented in the semantics. So therefore, when we add new features, we often do not need to revisit this existing definition. Okay, so I suggest that we take a short break for 5 minutes so we can go get some coffee, and we'll be back soon. And I will also be happy to take some questions during the break. So let's start at 40. So let's a 5-minute break and start at 42. So it's 37 now. Thank you. So any questions here?
Do we have a copy of the slides from your homepage? I haven't downloaded everything yet from your homepage.
A copy of the slides? Yes, yes. I actually let me do that now, so I can. So you do have the access to my homepage, right?
Yes.
So I can upload the slides there.
Okay.
Yes. Okay, so if you go to my homepage, in the ICFP 2020K tutorial section, there is a slides file, so you can get it. So I just post this the PowerPoint format. So after this talk, I'll update it with a PDF so it's more accessible. Okay, so let's start. Okay. Can you guys see my screen now?
Yes.
Okay. So we have showed the K definition of Lambda and Lambda++, and now we are going to do a much more complex language called Fun, and we'll define the complete K semantics for it together.
Do you want to just check everyone's back from their 5-minute break? I'm not sure if everyone is, but.
Oh, yeah, okay. Yeah, I don't know how to check it actually. So
maybe everyone can just react with the thumbs up if they're back.
All right, so how do you do it?
So when you move your mouse, then some of the controls show up like participants, share screen, and so on. One of them is reactions. You click on that and you should get a thumbs up icon.
Do you mean a chat or something? Because I don't see anything here.
Maybe it's only available with the desktop version of Zoom. I don't see it on the browser either.
Yeah. Anyway, I think everyone's back. So yeah, let me just start. So Fun. So Fun is a research language that captures the essence of functional programming paradigm. So it can be regarded as a very rich extension of Lambda++, but with many more challenging and interesting features. So everything in fun is an expression, and functions are first-class values. It has the built-in data types for integers and booleans and strings and also lists. And it also allows you to define user-defined inductive data types and to define recursive functions using letrec. And you can also do pattern matching over those constructors. And we also have callcc, and we also add mutables by means of the references. So on the right, I give you an example of fun program that calculates the maximum of a list. So as you can see it uses the letrec and fun, the keyword fun, to define recursive functions. And also the function definition is based on pattern matching, right? So we can match on the structure of the built-in list. So we'll start by defining the untyped dynamic semantics, which is good enough for us to execute well-typed programs. And later we'll show you how you can define type checkers and even type inferencers in K using the mechanism that you just saw. And at the end of the tutorial, I'll show you how to define the Hindley-Milner let polymorphic type inferencer in K. But for now, let's focus on the untyped semantics first. So let's not worry about the types. So if a program is ill-typed, its execution will get stuck because we will not give semantics if the types don't match. So we'll follow the K workflow, and let's write down some example programs for fun. So I've seen the first program. It defines the maximum function over a list. Let's look at the second program here. So it declares a data type tree, and the type is polymorphic, right? So it can take a type variable, and there are two constructors, one for leaf and one for the binary tree, the internal node. The leaf takes a data of type A, and the tree takes two trees whose types are, A tree. Then we can define a recursive function called mirror, which does pattern matching on the two data constructors, leaf and tree. If it is a leaf, then nothing happens. If it's a tree, then it mirrors the right subtree and put it to the left, and mirrors the left and put it to the right, right? So it mirrors, flipped the tree from the left-hand side and the right-hand side of the tree. The third program here at the bottom is similar, but here the data type pair takes two parameters and has only one constructor, pair. And the program is actually more interesting than the data type definition. It shows that functions are really first-class values in fun, right? So know that a let expression is used to define a function. So we can say let f and take some values and equals. That means we define f as a function. So it is a function taking two arguments and two pairs. And the first pair is a pair of two functions, a and b. And they will be applied to the second pair and get a sum. So for example, here we apply f on this pair. The result would be we calculate the sum of 10 times 20 and 10 plus 20, right? Because we'll apply these two functions on a pair respective and calculate the sum of the result. So the result for this program will be 230. Now let's take a look at the fourth program on the top. So it uses the references. So the function f takes two inputs, x and y, and it updates the value x by 2 and the value of y by 3 by looking up their locations. So so it will if we let x to be the variable that's corresponding to the location 0, the application fxx will first increase x by 2 and then increase x by 3. So, and then we get the value of x. So the result will be 5. And finally, let's look at the try-catch block. So to execute this program, we get into the the first try and get into the second try, and we execute this. So we have 3 plus throw of 10. And when we see a throw, this arrow will be captured by the catch here, the inner catch here. So we catch the 10, and then we throw 20, right? And that 20 will be catched by the outer catch. So we catch 20 and plus 1, so the result will be 21. So this is the try-catch block. We define it using callcc. So from these given programs, we can see that fun is in many ways like a real-world functional language. It has all the basic features and some of the interesting features. So in the demo folder, you will find many more programs. You can check it out. So now we are going to define the semantics of fun. Yes, Randall.
Sorry, I'm going to get a reputation for asking a question every 5 minutes. Like in something like Haskell, say your data type tree, you can use, you've got a different namespace for the data type and the constructors. So you can have them both with uppercase. Is there a way of getting K to handle that kind of syntax?
Yes, yes. So for this language, we are going to have lots of names. So, names for functions, names for data types, and we can choose, what whether we want them to be overlapped or distinct. So it's all, it's totally user defined. So we can define it. So I think here we are going to use the capital case for constructors and the lowercase for data types, so they will not be overlapped. But you can make them overlapped. Yes. Does that answer the question?
Yeah, no, cool. And I guess the other thing is, what if you required the constructors and data types to start with uppercase letters, Haskell as well, I guess.
Right. But then I think, if you do that, you will need more effort into the parsing, because you might end up with some parsing ambiguity. We'll see later, even for this this syntax we see here, there are already lots of parsing ambiguity, and we need some effort to dealing with those. So we see that very short. So we'll see it very soon.
Cool, thanks.
Yeah.
I have a follow-up question on the same topic.
Yes.
So earlier, when you showed us how to define the syntax for a language, we used the magic kvar name to define the identifiers. But now, if we do want to allow two different non-overlapping syntax categories for the data constructors and the type constructors, how would we specify that?
We can define them by writing down the regular expressions. So there is a way for K to define the tokens by writing down regular expressions and use them to define the syntactic categories. So previously we used kvar mainly because we are doing a substitution-based definition, and the predefined substitution module has this built-in sort called kvar, so we have to use it. But now we are doing an environment-based, so there is no need to use kvar, and we can define whatever tokens we like. It's totally user-defined.
Actually, do you have a definition of tokens handy?
Yes. Yeah, we have it here. Oh, the next, it's not here, but it's in here.
Here, okay, yeah.
So you see that there are many names. So we have the names and the constructor names, type variable. So all of them have different names. So we can define them as using this regular expression. So R means regular expression, and we give the regular expression, define the token.
Nice, thank you.
Okay. Right, so let's get back to the syntax. Right, so this is the program, so this is the syntax. So the syntax basically, so let's start with the names. So we talk about it. So there are many different names here, for various things. So we'll introduce them as needed in the talk. So for now, let's define just the function and the variable names, which we call them the name. So here, syntax name, we just declare it. We haven't defined it. So that its definition we just saw. It will be using the regular expression later. And then we also define the list of names. So it uses a built-in sort constructor called list. So it is a built-in in K. And what it does, it creates the sort names as the comma separated list of names. So it takes a base sort and a delimiter. And then we can define the basic expressions, the basic values and the parentheses for grouping. And we also define, expressions, the list of expressions. The strict attribute means that K will always try to evaluate a list of expressions into a list of values. And then we declare the sort val for values, and we define the sort vals for value lists. And then we can define the basic arithmetics and Boolean operations, and also if and else. So there are lots of them. And note that K provides a useful front-end notation that allows us to define them in groups. For example, the first three are also associative to the left. So we have a left here, so saying that all these are left. And the next three, they are also left associative, but they have lower priority. So we put a greater than symbol here to say that these have lower priority than the first three. And then we have some non-associative operators. In the attribute, we mark them as strict. And for the last two, they are strict of 1. So we have this the short circuit semantics here. So for example, if we see if we see false and something, we can evaluate that false without evaluating the second argument. So we have the short circuit semantics here for the Boolean operations. We also tag all these as arith, these operations as arith. So later, it's easier for us to define the global syntax priorities without a language constructs. And now we have the if then else, so it is the same like in Lambda. So this is the expression syntax of fun.
Right, so since can I go back a bit? Since you mentioned priorities.
Yes.
So the general mechanism under the hood is to set priorities and precedences between various syntactic productions. And this notation, where you can have like a group of productions, then larger than another group of production, larger than another group of production, this is very convenient. And this is not specific to K. Actually, we borrowed this from, do you remember from SDF or Rust or both? I think both of them have this. Yeah, so it's very convenient for small definitions to use a partial order as you define the syntax. But K has a general mechanism to define priorities between any two productions.
Right.
Just a quick question.
Yes. Mm-hmm.
On the strict of 1, for example, with and, if the first argument is true, then now is it the case that we're not, like the second argument might not be evaluated yet?
No, I think the rewriter will be, if the first argument is true, it rewrites the second argument.
Well, but that's a rule that will do that, explicit rule.
Yeah.
But just what we have here, you are right. So the first argument may evaluate to true, and the second argument is stuck. It's not evaluated. Or false, or anything, or 3, actually. The first evaluation to 3, it will get stuck there to be processed by semantic rules later on.
Right. Yes. Yeah. Okay, so now we define the syntax. Oh, Randall, yes.
Me again.
Yeah, go ahead.
So the question I have is, what if you want to do mix fix? So for example, you don't want to have if then be built in, but you actually want to define it as a function. So I think Agda has mix fix and can actually define if then else.
I think it is already mix fix, right? Because you write it like if the Boolean, then. So what do you mean by?
So what I mean is, so here we're defining if then else in the language syntax, but if we didn't, and if then else could be defined by the user as a user defined function, there's no reason why you can't do if then else as a user defined function for it. You just case split on the condition, and then you've got the true value and the false value. So it's a function that takes 3 values essentially.
Yeah. So it will be defined as a lambda expression, right? So lambda bool dot.
No, but so here we define if then else as a construct in the language, right? But imagine that you want to define an f identifier for a function which will allow arguments to be in mix fix notation, right? So it's like a 2-layer kind of mix fixness in K, which I don't think we support.
Not in this language, no.
When you say not in this language that we're defining here, or you can't do it, you can't use K to define a language that has that ability?
I think you would have to be creative. I think you can, if you allow a parser, which is a bit more generous than you would like to, and then define a a pass that would reject programs that don't make good use of the syntax. But the point is that K generates a parser at the beginning, right, for your whole language. It's not like a parser for each program in your language. Okay, so program where you define an F or a function, user-defined function, which is mixed fix, right? That would require parsing at runtime in some sense in K. And actually, K has, so the parser of K is hookable, right? You can hook the parser. You can call the parser of K at runtime. You need to do a bit more advanced programming in K, but that should be possible. Right? I mean, we define K in K. We have a project where we define K in K, and that includes all this parsing that K does, implemented in K itself.
Yes, self-hosted K. Yeah, that sounds cool. Yeah. Okay, thanks for that.
Okay, so let's keep going. And so we have the basic lists, the built-in lists and the user-defined constructors. So a list expression is simply a list of expressions put in a bracket and required to be a strict. So the expression list will be fully evaluated into a value list. And then we define the built-in list operation also as constant expressions. So the cons, head, tail, and now. And then we have this notation for appending a list. For example, so we can write something like this. So x1, xn, bar, t, which means the result of appending x1, xn to the list t, which is also a very useful notation. And then we define the constructor. So we first—
I think it's prepending, right? To put it in front.
Prepending, yeah, prepending, yeah. And then we declare the constructor name, sort, and we add them as expressions. So these are for the constant constructor, like nail or leaf or of a tree. And you can have a compound constructor which takes its arguments to build the actual term. It's a strict of 2, so the expression list will be fully evaluated to values. And now we have the syntax of lists and constructors, so pretty standard. Now we have function definitions and letrec. So I put 2 function definitions here, so we just saw them as examples. So in short, every function definition starts with the keyword fun, here, fun. And it followed by several cases statements. So each cases statement is like an expression, arrow the result. So the pattern, arrow the result. So we define a case as this. So a case is an expression, arrow the expression, and cases is just a list of cases separated by the vertical bar. And the function definition is just a fun followed by the cases, right? And then we have the function application, which is like in Lambda, it is strict and it's left associative. We also have let and letrec. And in fun, we allow them to take a list of bindings, right? So the bindings is, x is bound to this expression and y is bound to this expression. And we can have many of them in one let or letrec. So we define that syntax as shown on the left. And bindings is simply a list of binding and separated with the keyword and. So we have let x equals something and y equals something and so on. So that's for function definitions and let and letrec and the cases syntax. Now we have references. So we first define ref as a constant expression. So it's like a constant function that can be applied to expressions. Its semantics is that it takes an expression, evaluates it into a value, and stores the result value at a fresh location in the store and return that fresh location, that reference. So later we can access the value by looking up that location. So we also have the at construct, which takes a reference and a location value and returns the value stored in that location. So we also add a new auxiliary construct called the AND constructor. It is like the pointer constructor in C, the dereferencer in C, which takes a variable name and it returns the location. So the purpose of adding this construct is to help us define the semantics of ref. However, we know that having this C-like pointer construct is quite controversial to a functional language. So we only show, so here we just show one possible way of defining the semantics. So it's totally okay to define it without, introducing this AND construct. And then we have a location update construct, this colon equal thing. It is strict in both arguments. So the first should be a reference, a location, and the second should be a value. And the semantics of that is it will update the reference with a given value. And finally, now we have expressions that have side effects. We define a sequential composition construct, which is right associative, and it's strict at the first argument. So this will let K to evaluate the expression one by one, right, from left to right, which will give us the intended semantics. And that's it for the references. Any questions about this? Okay. So callcc, we saw that. And our plan is to define try-catch block as a syntactic sugar using callcc. So we'll see how to do it later. And yeah, so basically that's it. We have the callcc, and we also add the try-catch block. And we define throw as a token. And we'll see why. And the main, in short, the reason is that we will desugar try-catch into the function of callcc, and throw is just a special function name. So whenever you see throw, you just trigger the callcc, on the external continuation. So we'll see an example later. So we have polymorphic data types. We allow expressions to have a data type definition at the beginning, so like this. And each data type declaration has a form data type equals a type cases. And now we can have a type variable, which is here. So type variables are the prime A, prime B on the right, so they are type variables. And a type can be either a built-in type, int, bool, string, or it can be a function type, an arrow type. It can be grouped using parentheses. It's either a variable or a constant type, or it is a constructor type, a type name instantiated by the concrete type, or a type name instantiated by a list of types like the pair on the right. So it takes two types here to be instantiated. And now a type case is simply a constructor, so a constant type, or a constructor takes some more types. So like the tree here, the leaf takes a type and tree takes two types here. And the type cases is just a type case separated by the vertical bar. So now we have the data type syntax defined in K. But note that we're defining a dynamic semantics here, which is untyped. So this will only be used when we define the type system for fun later. We're almost done with the syntax. So we define some global priorities between the language constructs. So there's a way to define them in one place. So we have a syntax and priorities, and we list them in order. So this has the highest priority, followed by this, which is a function application, and all the arithmetic operations. So this is the user tag we give when we define all the arithmetic operations, and then assignment and lettering and all this. So in order. All right, so we talk about this. So there's a way for K to define tokens using any regular expression. So a name will start with a lowercase, and the type variable has to start with the prime as the first letter, and so on. And now let's see some macros. So this is also the last part of the syntax definition. So for example, the head function for list would be desugared to the function that matches a non-empty list and returns the head of it. So the head is actually a function found that matches on this pattern. So the head and the tail, and it returns the head of it. And the tail just returns the tail, and so on. So the prepending operation will be defined as in a recursive way, right, by nesting itself. And this is a multi-argument function definition. So it can be desugared into single argument functions, right? So if we see P1, found P1, P2, arrow E, it will be found P1, arrow found P2, arrow E. And we can use a binding like this to define as a function. So instead of saying that let F equals found something, we can say let F P1, P2 equals E to define a function for F. So it's also a syntactic sugar. Now let's see how we can define try-catch using callcc. So recall that the semantics of try-catch is to evaluate try. And whenever we see throw, we jump back to catch, right? So if we don't see a throw, we'll finish the evaluation normally and keep going. So to evaluate try E, catch X, E prime, we'll call callcc. By calling callcc, we'll remember the current continuation in which the try-catch is called, right? So we can get back to it in the future. And this continuation, the current continuation, will be parsed to the parameter $k, right? So now $k has been instantiated to the current continuation. So what happens next is that we evaluate the body, right? So we'll apply this function to this function. So what does it mean? It means that by beta reduction, right, we'll evaluate E, but we'll replace the token throw by the function found X arrow $k E prime. And here we have two cases. The first case is when we evaluate E successfully to the end without calling throw. Then when we finish, the entire callcc finishes, right? So we keep going with the original continuation, right? So the callcc never eliminates the original continuation at the end, it's still there. So whenever the callcc finishes, we'll keep going, right? So that's when we finish the try and we don't throw anything, we just keep going with the regular computation. The other case is when we evaluating E, which is the try part, right? The try block, when we evaluate it, we see a throw, right? Throw of value V. Then we'll follow the semantics of throw, which is this function, right? So we'll instantiate this X by the value of V that we throw, and we apply the continuation to, we apply a continuation to E prime, which is the catch block. So we evaluate the catch block, but the parameter X has been instantiated by the value V that we throw, right? So the $k is the original continuation. So we'll start to evaluate E prime, which is the catch block, but X is replaced by the value V that we throw. So in one rule, we desugar try-catch into callcc, right? So it's a quite complex semantics, but it's also very compact, right? And all this happens before the semantics, before the actual application of semantic rules. It's a macro rule, so it's really a syntactic sugar definition.
Can you explain why you're defining new dollar variables instead of using regular variables in those definitions?
I think it's mainly for parsing issue because we need a way to, because this phase will be, it's essentially a desugaring phase. So we need to give some fresh variable names for K to use when it applies the macro definition, because we need a name for the bound variable $k here, right? So I think it's mainly for parsing issue. As far as
also that dollar, so a user cannot define variable names starting with dollar. Right? So the parser will reject any programs whose variable names start with $. So we know for sure that these variables $k, $v are reserved to the semantics. So it's a bit of cheating. We are extending the syntax of names with some names that we want to use in the semantics, but the users are disallowed to, the parser will disallow users to use such names themselves in the programs.
Right.
Thank you.
Sorry, a clarifying question, if it's possible.
Yes.
So how does K then distinguish between the syntax rules that are meant to be used by the end user, so by somebody who writes the program, and the syntax rules that are only meant to be used inside the desugaring?
We put them in different modules. I didn't show you the modules here, but we'll have a syntax module which defines the syntax, and we'll have other modules, for the semantics. And there you can actually extend the syntax as you want, but K will not use that part to parse the user programs.
So one of the reasons the compile command takes so long is that it generates several parsers. So there is a parser for programs that is generated from a particular module, the module containing syntax on it. And then there is another parser for the semantics. So the parser that parses these semantic rules that we see on this slide, includes all the syntax of your programming language and the syntax of K and the syntax defined in this module that is being parsed. Okay, so this syntax production, name equals $k and $v. So this is now included in the syntax from which the parser that parses these rules is generated.
Mm-hmm.
We try to avoid explaining all this complexity of parsing if we don't have to, but since you asked,
yeah.
Okay, thank you. I appreciate it.
Right. Yes, Randall.
Sorry, there's two of us in the same room here, so the head and tail that you've put in the syntax, there's no reason why those couldn't be left out and just defined by the user, right?
Yes, yeah.
I mean,
they're convenient. They're convenient.
Yes, but the user will need to write this font all the time, right? Whenever they want to use a head.
Yeah, I guess it could go into a library, but we don't have the concept of import or anything like that. Right.
Yes,
okay.
Yes. All right, so that's a syntax, and for the configuration, it's the same as in Lambda++. So we have a K cell and the environment cell and the store, and that's it. So I think we're a little bit behind the schedule, but still I want to show you the demo 4, which is the desugaring of the try-catch block, how we can desugar it. So let me go to the demo 4. All right, so just to save some time, I won't run it. So you can see on the right, so the results. So there's a, it just, remember that we only have a syntax, so we only have the parser here, but we have the macro definition, so we can desugar, programs into, into their primitive form. So there is a program called list1. So it just, let second to be, you take the tail first and you take the head of the list. And we can ask K to execute it for 0 steps. So what K would do is to basically parse the program and expand all the macros in it. So this would be the result if you run the command. And you'll see that there are pending some nils pending at the end of the list. So if we rewrite it manually into a much nicer form, it will be something like this, right? So the second, let second equals fun. Note that we have this fun keyword here to define a function L. Rewrites to apply this function, which is a head function, on the result of applying this function, the tail function on L, right? So that's how, which is expected. let's also see the try catch block. So we have a throw here, and you know what it should do, as I said, is to evaluate the most inner try, and whenever it see a throw, it will jump to the inner catch here, and this throw will be jumped into the outer catch here. So if we ask K to desugar this, as 0 we run it for 0 step, we'll end up with the definition that looks like this, right? So it will be a callcc on the function, right? So then the semantics of callcc is to apply this function on the current continuation, right? So we apply this function on the current continuation, and by beta reduction, we get into the body where $k1 becomes, you know, where the try catch block is called. And then we have a function application. So we apply this to this. And what does it mean is by beta reduction, we'll evaluate the body, right? Which is the inner continuation. So the inner callcc, the inner try block. But the throw, so you see the throw one here, the throw will be this function. So whatever things that we throw will be captured by this x, and we'll calculate x plus 1 because that's the outer catch. And after that, we continue, right, with the outmost continuation. So that's the first, you know, the outmost try block. And this callcc is just the inner try catch block, right? So when we call it, it will remember the current continuation, right, inside the first try, and K2 would be that continuation. And we apply this function throw2, you know, found throw2 to this. So meaning that we'll evaluate the body, you know, 3 plus throw2 of 10 plus 2, which is the inner try block. And whenever we see throw2, we'll jump to this function, right? So this is the inner try, this is the inner try. The inner catch block, this is the inner try block, and this is the inner catch block, right? So this is how we desugar try catch into callcc. All right, so let's go to the semantics. But before that, do we have any questions about the syntax and configuration? So just to say that the point of showing the callcc is really to show you, for tricky language features, the K definition can be really compact, and still it's a rigorous semantic definition. Okay, so let's start with the semantics. So some simple ones here. So for arithmetic operations and Boolean operations and all that. So actually none of them are, so they are both from Lambda plus plus, so, and we don't need to change them. Functions and closures are almost the same, but this time functions are defined using cases. So we need a pattern matching here. So the semantics of pattern matching, so you see the function cases related to the closure as we see before, but now the closure takes not the body, but the cases. So the cases becomes the body. And what happens when we apply a closure, the function closure, to a value, is that we are going to add new tasks here, which is the pattern matching task, and we'll match the cases one by one, right? So this rule says we'll try the first case because P arrow whatever, this is the first case in the list of cases. So we'll try that. We'll try to match P with V, and there are two results, right? So if we succeed, we'll have this get this match result, which holding the solution, and we'll bind that solution to the environment, and we evaluate E in that new environment, and after that we set back environment to the original environment, right? So that's when the pattern matching succeeds. If it fails, then we'll try the second, right? So if it fails, then we drop the first one, and we'll just try the rest cases. So that's pretty much it. So we have some auxiliary definition like get matching and bind map. So we'll talk about get matching later. So let's see the get map, bind map here. So when we have a successful matching, we'll have a mapping from variables to their values, right? And what we're going to do is to add these values to the environment. So, and the way that we do that is we match the first binding and we delete it. So we write it to empty main. That's how we delete a thing in K. And then we create in the environment a new fresh location for that variable. And in the store cell, we assign that location to V. So that's how we create, bind a mapping into the environment. And we just keep doing it, go through all the maps, all the bindings there. And once we do that, we have all the parameters, mapping to the right values according to the matching result. And then we evaluate the expression E. So that's how we evaluate the function through pattern matching. We haven't defined get matching, so let's define it. It's pretty long, but it's very straightforward. And there is almost nothing deep about it. It just looks pretty long. So first we define functions get matching, and we need to merge two matchings, and so also the two match results, either success or failure. And get matching auxiliary is the list of, the list version of get matching. So it matches a list of expressions with a list of values. It's pretty.
Maybe you should skip it, Shahon, because
yeah, okay.
You have more to talk about, and it's not necessarily the best way to do it.
Right.
We
okay.
used to have a meta-level definition of matching that would work with all syntaxes for all languages. Now this one is concretized to this particular language syntax, which is a bit suboptimal.
Okay. So we have letrec. So let's talk about that briefly. So we used to see letrec by desugaring to Lambda, but we can give them a direct semantics, so it's clear to see the difference. So let will first bind names to the values, and then evaluate the expression, and then restore the environment. So the difference is that letrec will just bind the names, and then assign the values to those names and keep going. And what's the difference? So you see the bind to is defined here. So it's a bind to, it's a strict of 2, right? So what it's doing is it will evaluate the second arguments into values. And then it will bind those values to the variables. And when you evaluate the values, you're evaluating the current environment, right? So in the old environment. And then you update the environment with these new bindings. That's how you do a let. But letrec is different. So letrec first just bind the names. So you see the bind names, it just assign new fresh locations to names without their values. So they don't have a value yet. They just have their registers in the environment. And now we apply this assign to, which is a strict of 2 construct. And then we evaluate expression. So the expressions here are evaluated after all the binding variables are registered in the environment. And the purpose of doing that is we are going to have recursive calls of those binding variables. And when we evaluate those, the closures, the function closer generators know about all these pointers of functions, right? And then they can, call themselves. That's how we do closures. So basically, let means evaluate the expression in the old environment and assign the values to the variables. But letrec means to first assign those binding variables of fresh locations. And then in that new environment, you evaluate the expressions and they get the closures, right? So the closures know about these new locations. And then you assign names, those locations to the closures, the values, so that you can call, a function can call itself. So basically, that's it. It's just a different way to define let and letrec, but it shows very clear, why they are different.
So once you have the infrastructure, you know, for all these bindings and binding maps and so on, assignments, then we can define them each in one rule.
In one rule, we don't need the bottom part. Yeah.
And also several other constructs, I think, also make use of this.
Right.
They are quite common to have, like in a library, all these bind to, and so on constructs.
Right.
I think we use them in the K tutorial. Not this tutorial. The K framework has a tutorial. This is part of that tutorial. Has several languages making use of this bind to, get matching, match result, and so on. So students kind of got used to them, but now I realize that, you know, they need some explanations.
Yeah. All right. So we have references. So they are quite simple. If you remember, ref is just to get the location. So we desugar it to this this AND construct, and for AND, we just look up the location in the environment cell, and add to look up the value in a store cell, and you know, this location assignment is just look up the location in the store cell and change its value, and then sequential composition is just you know, remember that it is a strict of 1. So the first argument is going to be evaluated first anyway. And when it gets to the value, we drop the value and rewrite it, you know, start to evaluate the second.
You could use an underscore there, right?
Yeah, I can use an underscore for the first part. Yeah. Yeah.
This is a very fortunate case where we have just one rule per language construct. Because this is a pedagogical language. But when you have real languages, sometimes you need 2 or 3, sometimes even more rules per language construct.
Right, right. Okay, so that's references. So we have callcc, and it's the same in Lambda. So even if we made so much extension, so we don't need to change existing rules. So because we don't touch how, you know, environment is used in semantics, so we just keep this rule. So now we finish the semantics of found. I think now is some time to do the demo, and we can get into the type system. Yeah. Let me show the demo 5. And by the way, all this README and demos, you can find it on my homepage. So so let's do some interesting ones. So we have this list is expected. So let's see that we can do constructor days. So this is an example function program. So we can define constructors. All these are constant constructors, and we can define day after. Using pattern matching, and define, you know, calculates what is the day after a few days in a recursive way, and then we can call it. And the result of executing it is this, as expected. But you'll see that there are many things in the store cell, right? So that's a result of evaluating function closures. So we keep adding things to the store. So it'll be there. It'll be interesting to see how. Is it possible to have some garbage collection here? So actually, it's longer than this. I can show you quickly. Programs, constructor, base.
Yeah, so there are 2 ways to think of the garbage collector. There's a garbage collector in K itself, right? So when certain subterms are not used anymore, they are garbage collected by the K engine. But then you may have garbage collection in your language,
yeah.
Where literally you have to give it a semantics, because it's not clear what it means. You know, it's not clear that you can remove those locations from the store, unless I mean that. Yeah, so basically you have to give a semantics to the garbage collector, and then you have it in the execution engine.
Right. The
reason why it's interesting to know if you can generate automatically a semantics with garbage collection in it based on some higher level principles.
The reason why it is not obvious to know whether you can remove entry is you have some closures, right? So in the closures that there may be references to those locations. So we need, yeah, we need a formal semantics for garbage collection. Okay, and then we have the tree example, which I won't run it, but you can see it. It's still pretty much the same idea. So we end up with an empty map. That's where we start, and in the store we have lots of things here. So I think I don't need to go through each of these programs, so you can just run it. So the point of showing this is to show the polymorphism. So you'll see that we have we define a function which is the identity function, and the value of it is a closure. It's a closure value, so we can apply it to other things. So later it becomes interesting because we see that this is a this function f is polymorphic because it can be applied to any arguments. So it becomes interesting when we define the type system. So I'll finish it with one last example about stuck letrec. So let's see this program. So let x equals 1 in letrec x equals 2 and y equals x in y. So what will happen when we evaluate this program? We'll see something like this. So basically it gets stuck. And the reason why it gets stuck is how, the difference between let and letrec we just talked about. So letrec will evaluate the right-hand side by assigning x a new fresh location, but not give it a value, right? So what happens is when we evaluate this, K will first K will first give x a fresh location, and then evaluate 2, and then give a y a fresh location and evaluate x. But when it evaluates x is assigned to a new fresh location which has no value, so that's why it gets stuck. So basically it says I don't know the value of x because it's not in the store. You see that x maps to 2, but there's 2 maps to nothing here in the store, and that's how letrec is different from let. All right, so let's get back to the tutorial overview, and we'll get to the last part of our talk, which is to define type system. So what we just saw is, the semantics of fun is untyped, but we can define type system as well. But just to keep things simple, I would just show you how to define types of Lambda, and the basic principles can be applied to do fun, and we'll put it at the end of the talk. So let's defining type systems in K. So the key observation here is that so the dynamic semantic we just saw uses the rewrite rules to evaluate programs and expressions to concrete values. And type systems are the same. So they evaluate, they use rewrite rules to evaluate programs and expression to their types. So in other words, types becomes the concrete values now. And besides that, the main idea is the same. So we'll still use configurations to organize not semantic information, but typing information, right? That will be needed during the typing process. So in the following, for simplicity, we use Lambda as an example. I'll start by showing you how to define a type checker first. This means that we'll assign a type to each variable used in the Lambda program. So the K definition only needs to check whether the given types are correct or not. So this is rather simple. And then we'll get into type inference. So this way, we'll eliminate the types from the variables, and we'll let K to infer the types of the variables from the way they're used in the program. And we'll discuss several types of inferencers. So there is a basic, a very naive one, and there is a polymorphic one, and we'll end up with this let polymorphic type inferencer for Lambda, which is probably the most popular, the standard type inferencer. All right, so let's start with something simple, so which is to define the type checker for Lambda. So it is a type checker, so the variable has a type. So you see the Lambda x colon type has a type associated with it. So let us define what is called the simply typed lambda calculus, which means that the types here are either the basic types or the arrow type for functions, right? There are no polymorphic types in this calculus. And now we want to define rewrite rules that will write an expression to its type. And therefore, let us include type in the expression and define that k result is also a type here. So types are results, right? And then things become simple because, for example, whenever we see a lambda, so we know it is a function of the arrow type. So t arrow e, right? So and k will evaluate e to its type, right? And when and during this rewrite, we'll update the typing environment from row to row, where we add the binding x has type t, because we know that in E, x has type t. So that's pretty much like a well, it doesn't look like a beta reduction, but it is still very straightforward. So, a very straightforward way to type a lambda. And also, whenever we see ID, we look up this type in the type environment. And for application, we require that the function type and the argument type matches, right? So T1 and the T1 here, there must be the same type. And the result is T2. So for arithmetic operations, we will rewrite integers to the type int, Boolean value to the type bool, and arithmetic expressions to their types. Very straightforward. And also note that the concrete values are no longer k results, right? And they're not the evaluation results. So the types are evaluation results now. And also, if and else, the typing rule for that is if bool, then a type, else a type. And the point is these two types must be the same. So the if and else is no longer strict of one. It is strict in all arguments, right? Because we want to type all three arguments, and then we can know if this if and else statement is well typed. And also for let, we'll reduce it to lambda, and we'll apply the typing rules for lambda and function application. For letrec, we'll reduce it to let and mu, as we saw in lambda. And for mu, it's pretty much like lambda. So whenever we see mu, we know immediately it is a function, right? So it is a function type, t arrow t, but we need to make sure that E has the same type as x, t, with the assumption that x has type E. So this is a very smart way to doing so, right? So we rewrite this into a function application. So the function type, t arrow t, apply to E. And now, okay, we'll evaluate the type of E in this updated environment where the binding variable x has type t already. So if this rule is successful, we know that the mu is well typed and the type will be t, right? So any question about this rule? So I think this is probably the only non-trivial rule in this entire definition, how to type a mu. It's a very smart way to do so. So yeah, and this is just how we restore the typing environment once we typed a lambda or a mu. So this is quite, so we also saw similar rules in the previous semantics. So now we have the type checker. So let me see how much time we have. I think we have enough time for a demo use. I will do a demo. Yeah. All right, so we can see the program, the factorial program, for example, and it is a factorial program. And the difference is that we associate the type with all the variable. So k doesn't infer them, so we give k to it. And if we run it, we'll get the result int, right? and we can run it step by step. So what we do is the first letrec will be desugared into mu, right? And it will be desugared into mu, and then K will start to type mu. And we know that the mu is a function from int to int, right? So what we're going to do here is to create this this type int, this int to int to int, because that will be the type of a function, not of a function f, but we'll try to apply this to the lambda, right? And we hope that we'll type lambda also as int to int, right? That's the only case where we can resolve the entire thing, right? So, and also that when we type lambda, we know that f is type int to int, right? So that's how the recursion happens here. So we will type f, and then we'll type the body. We want to type in the same type of f with the additional knowledge that f has this type. So that's where the recursion comes in, right? Okay. So the type checker. So any questions before we move on to the type inference?
Not a question, more like a comment I'd like to make here. Since we've shown such definitions of type systems in the past to various colleagues, one of the main reactions was that type systems are typically not defined this way. Type systems are typically defined in a big step-like style, where you say that in this type environment, this expression has this type, right? And then based on that, you define how types propagate to various language constructs. So what you see here is a small step semantics of a type system, where, right, an integer value, like you have this first rule, right? An integer value writes to the type int, then, so 7 writes to int, then you gradually replace the program, rewrite the program to its type. And that may look very strange to some type theorists, because you want to keep separation between syntax and types. You don't mix them together. But in fact, what's interesting is that at the end, if everything goes well during the typing, small step-ish typing process, in the end, you get a type anyway. And if you somehow refrain from this, idea, or if you accept that this might work, right? Then when you look at the definition, this definition looks quite intuitive. In fact, it's hard to imagine anything more compact than int plus int writes to int when defining the typing policy of plus. Right? Or if you look at if then else, you will say if bool then t else t writes to t, right? So this is a very nice way to say this is a typing policy of if then else. So small step type checking is pretty interesting, actually, pretty feasible. And in our case with K, it follows it falls into the same general philosophy that type system is just a semantics like anything else for a certain syntax, but a semantics in a certain domain, that of types. And this is not unheard of. Abstract interpretation also looks at things in a similar way. It's just that this small step style, right, where in intermediate steps you have syntax of programs and syntax of types all mixed together, and that some people may find that unusual, and I just wanted to point this out.
And just a comment that it is also possible to do a traditional big step typing in K, right? It's just it's not impossible to do that. It's still possible to do it, but it's just that we prefer more this small step style because it's more compact and it's intuitive.
And you can use the same tooling that K already has efficiently.
Yeah.
I have a few questions.
Yes, please.
So you defined the sort k result, but I don't see it used anywhere. Is it another magic source that has some special meaning for k?
Yeah, it is a built-in sort for k. So k looks at the values in this sort to know when to stop evaluation things.
So it's related to the strictness attributes. But when you say that an operation is strict on certain argument, how do you know when to stop searching for rewrites on that argument? So when it reaches k result, it stops.
Thank you. And I have another question. Can you explain the twiddle arrow again? I thought it was like capturing the future rewriting steps, but now, for example, in the rule for Lambda on the left, you're reusing row several times, both in K and TM. That's not what I expected with my previous understanding. So clearly my understanding is wrong. So can you explain it again?
So to read this rule, so we have a lambda to type, and we know it's going to be a function type. So we write it to T arrow E, but it's not typed yet, right? So we still need to type E. But when we type E, we extend the current typing environment, right? So by letting X to have this type T, because now we are in the body of the function, we know the parameter has type T, right? So that's the first part of the rewrite. And once we—
It's also the fact that there are two rewrites here. So maybe an easier way to read it is to ignore everything after the rewrite relation in each of the cells. So that shows that the context that you match. So you match a context where you have lambda x t dot e in the K cell, and you have raw. You match the entire contents of the T, E, and V, the type environment cell. And then each of them gets rewritten to something. So raw gets updated to row where X is updated to T, and lambda x t dot e gets written to the type T arrow E, followed by, this is a different arrow, followed by raw, and this followed by raw is defined somewhere, right there. That basically says that when you are done with evaluating whatever is before that row, then update the type environment. Don't forget to type to restore the type environment to raw.
So is this twiddle arrow just another piece of syntax that you're rewriting like everything else? It's not a K built-in?
Yes, yeah, just like any other syntax, but it's a predefined syntax in K.
Okay, thank you.
But if you don't like that arrow, you can define your own with the same semantics.
Right. Okay, so thanks for the questions. So let's get into typing inferences. So for now, we still consider simply type system for Lambda, but this time we'll remove the types in the Lambda abstraction. So we need to infer those types from the way they're used in the program. And in short, each usage will generate a type constraint. So by traversing the program, we can collect these typing constraints. And if there is a common solution to all the constraints, then we say the program is well typed. And if the constraints are inconsistent, then the program is not well typed. So typing inference is essentially constraint solving, or more precisely, the type equality constraint solving. So we use the following example to show this. So we have a program with 3 variables, so x, f, and y. We have 3 variables here. And we don't know their types, so we have to infer them. And the first variable x can be any type. So let's assign the type variable alpha to it, or the prime a means alpha to it, and keep going. And now we see a function, let f, which is a function, right? So, so if we apply the semantics of let, so we end up with this, something like this, because it's let f in f itself, right? So it would just be this. And now we see a lambda y. And again, we need to assign, we don't know the type of y, we need to assign a new type variable beta to it for now. So we end up with this. So it's a function from alpha to beta to the body of it. And then we see this application alpha applied to 7 and alpha applied to b. And we know that we can do it only if alpha is a function type, right? So that's when we add this constraint. So we say that alpha must be of a function type alpha A1, arrow alpha A2. And then because it's applied to 7, alpha A1 must equal to int. And because it's applied to beta, alpha A1 must also be beta. So we start to collect these typing constraints along we type the program, right? And then we end up with this type. So everything is a type variable, but we have a type constraints. And then we can apply this type constraints, simplify it, we get the result type, which is int, arrow alpha 2, arrow int, arrow alpha 2. So you can see it because the alpha will be alpha 1, arrow alpha 2, and alpha 1 is int, alpha 2 is still fresh, so it can be anything. And the beta type is alpha 1, and alpha 1 is int, so it's this type. So essentially, type inference is basically solving equations like this, right, among types. And in computer science, solving equations is called unification. So we use unification to implement type inferences in K. So let's see one actual definition. So let us now define a naive type inferencer for Lambda. So we'll keep the simply typed system. We see that the types which are defined here. So the types here are still the simply types. So they're either basic types or the arrow types. They're not polymorphic types. But now we need to infer the type of the ID because we remove the types in the Lambda abstraction. So to do that, we'll use the predefined K module called unification here. So we import unification. So it provides equational solving to implement a type inferencer. And to use the equational solver, we simply put equations as computation tasks in the K cell. So let's see where you can see it. So here. So we define an equational task between types as a K item. So we'll be putting the K cell. And what it will do is the unification module will automatically collect these constraints and calculate the solution. So in unification, it's called a most general unifier, but essentially it's a solution of all the constraints you currently have, the most general solution. And using the unification term, it's called a most general unifier. And let's see this rule on the right. So it types an arithmetic expression. So what it does is whenever we see T1 times T2, we'll generate two constraints, right? T1 equals int, and then T2 equals int, and then int, right? So it means that we'll add this constraint T1 equals int to K, right? To the internal unifier, and T2 equals int to the internal unifier. And if there is a solution, then we know the result is int, right? Because it's an arithmetic operation. The type of it is int. Or if it has no solution, we can tell from the K, from the configuration, because we'll see a get stuck somewhere, right? The K will say that the unification has failed, so it is not typed. It is not well typed. And now we have the typing of Lambda. So recall that when we type Lambda, we need to assign the binding variable a type variable, right? So we just saw that because we don't know the type of the variable, so we have to give it a type variable in it. So in K, we can do that by using this question mark T notation. So what it does is it would generate for X, the variable X, a fresh type variable T, and it will assign it to the typing environment. And with this new assignment, this new typing information, we'll type E and set the environment back. So it's a usual thing, but the only difference is that we now can assign, ask K to generate a fresh variable and assign it to the binding variable X here. For another example, let's see here, the typing rule for application. So it guesses the return type for T1, right? So whenever we see T1 apply to T2, we know that T1 has to be an arrow type, but we don't know the return type of that arrow type. We just know that the argument type has to be T2, right? So we'll guess a type variable for the return type, which is question mark T, and we'll add this equality, right? T1 equals to this arrow type from T2 to some type, I don't know. And the result is that type, right? So what it does, it will add this equational constraint to the solver and then return this variable. So, whose value may be determined by the collected equational constraints. So that's basically how K do things. And to sum up, this naive type inferencer is still quite simple. And compared to the type checker, it does the same operations, but with two important differences. So first, instead of declaring a type which each declare variable, so we assume a fresh type for that variable. So this is in the Lambda. And second, instead of checking that the types of expressions satisfy the type properties which they are used, we will impose those properties as type equality constraints. As we type the programs, as we traverse the program, we'll collect these typing properties. And then we use a general purpose unification based solver to solve these constraints. So I can show you some demos, but before that, do we have any questions about this definition? Okay, so let me show some demos about it. Okay, so let me get to the README 7. So let's see this identity program. So you can see it on the right. So we have a let f in f1. And the type of it will be int, obviously, because f is an identity function. And what is interesting is some of the execution snapshot that I posted here, so we don't need to rerun it. So you see that during the typing, we'll generate a fresh variable for x because we don't know the value for x, right? So we will just generating it. So you see that f is assigned to a type variable called v0, and then v0 is typed to int, right? And then the next step, you will see that we add this new constraint, v0 equals to int arrow v1 to the K cell. And why? Because we now see this application. So v0 has to be an error type, from int to something I don't know. So we generate a new fresh variable, and the result is v1, right? And after that, you will see that f is now has a function type, right? Because now, previously f maps to v0, and now I have this constraint v0 is this arrow type. So in the next step, f has this function type, and the result is v0. Just note that K automatically renamed these variable names. So the v0 below is actually a v1 above, because K automatically renamed those. But the idea is here. So as K executes semantics, it will collect these equational constraints and add it to a solver. And the solver will update the value automatically for us, the unification based the solver. Okay. All right. So so there are some limitations of this naive type inferencer. So let's see these two programs. The question is, can we type them? Let's look at the first program. So we have let ID equals identity program. And we have an if then else statement. So we apply ID to true, but then we apply ID to 1 and 2, right? So if we follow this naive type inferencer, what will happen is that from this we'll know that this ID is a function from some type alpha to alpha. And then when we see this, right, we'll generate a new equality saying that alpha equals to bool. And then when we see this, we'll generate another equality saying that alpha equals to int. So we'll have an inconsistency, right? Because bool equals int is not solvable. So we have an inconsistency. So this program is not well typed in this naive typing inferencer. And the reason is that we have this inconsistency here.
Your slide says.
Sorry, what? Is that a question?
Don't worry.
Okay. All right. So let's look at the second example. So we have the same identity function, but this time we apply ID to itself. And let's imagine, let's assume that, imagine that we are the type inferencer. And what we're doing is we'll assign the type, the function type, alpha to ID. And then we'll have alpha to alpha applied to alpha, right? And by the typing rule of the application, this means that we need to type alpha equals alpha to alpha, right? Which is not possible because we're in a simply typed system. So, alpha is not equal to the function type alpha to alpha. So it has no solution. And, but these programs they make sense. So we still want to type them. So what we want to do here is to introduce polymorphic types. So an expression such as ID can have different type instances, even in the same expression, right? So even in the same expression, different occurrences of ID can have different instances because that's an identity function. It can be applied to arguments of different types. And that leads us to the polymorphic type inferencer, which we'll define later. So here, so the polymorphic type inferencer is actually, it's very simple. So we already know the problems we count type, these programs is that when we see a let, so let me go back to the previous case. So when we see a let, we rewrite into lambda, and that means we'll assign x one type variable, so a fixed one, and there will be everywhere in the body. So we use one type for x in all E everywhere. And that causes a problem because here we want x to be of different type. Here we want a parameter to be of type bool, want the type of parameter to be of int here. So we simply change the let into substitution, right? And so whenever we see a let, we, instead of desugaring into lambda, we desugar it directly into this substitution, which looks at a beta reduction. And the reason why it solves our polymorphic problem is by beta reduction, we replace all the copies of the binding variable x by the copies of the expression E themselves in E prime. So now we have lots of not variable x, but lots of expressions, many E's, right, in E prime. And each E can be typed differently. So for example, the first program will be sugared, this program will be sugared not to lambda abstraction, but into if lambda xx apply to true, then lambda xx apply to 1, and so on. And we can type the first one, right? We can type the second one separately. So they don't need to be of the same parameter types. They can be separate. So in that way, we solve the polymorphic type we can handle the polymorphic types. Let's look at the last problem here. So can we type this program using this polymorphic type inferencer? So this is a lambda x, and then let f be the identity function in let d be apply f plus 1. And this is important, right? So we know that the value of d, the type of d, must be an integer in x. Yes, Brandon?
In your solution there, though, don't you now get multiple definitions of ID, or the lambda anyway, which are actually the same? So you get duplication that's unnecessary?
You mean here in this row?
Yeah.
Why is duplicate?
Because you've got ID, in your example, you've got then ID1 and else ID2. Both of those IDs are going to be the same type. And they're actually the exact same ID, but each time they occur, they're so you're going to desugar ID into the let, right?
I desugar the ID into the
maybe I just
into the
misunderstood
into the lambda.
But that is really the problem, because now you will type E many different times and you'll accumulate the same constraints. mostly for E all the time with slight differences in each instance, right? So there are, I probably don't have time to talk about that, but there are future lessons, versions of this inferencer where you have type schemas, right? You type E and get a type schema out of it, and then you instantiate the type schema at each instance, each you know, for each X, as opposed to retyping E in each place.
So
okay,
yeah, I think what we're really talking about this is this. So let's skip this. So is this DHM type inferencer? So,
Yeah.
and yeah, we'll end up with this one. So so let me just quickly show. Yeah, let's just show the definition. So this is so this is
the right way to do it. The right way to do it.
Yeah, the right way to do it. So let me start with these slides, right? So we have this program, and if we type it using the previous polymorphic type system, and because of beta reduction, it will type it as let me just go to previous slide. It will type it into alpha type arrow alpha, and the reason why is this let d is never used, because by beta reduction, you know, you keep going. You know, we have a lambda, we have a t arrow because of function, we have a t arrow and the lamb at the let, and then we do the beta reduction. We have the inner let, and this inner let is never used because d is not using the body, so it becomes just t arrow x, and x is, you know, t is the type of x that we give it, is the type variable, so it's t arrow t. But if you look at it, you know, in a closer look, you realize that it should actually be int arrow int, because you know, we can follow this step, and you know, now f is an identity function with a type t arrow t, and then in D we know that f will be applied to the variable x, and the result of it has to be an integer because I need to apply the result with +1. So f in that instance has to have type int to int, not var to not alpha to alpha any type, but int to int. And as a result, the x must have type int, and the entire function must have int to int. So this is the right way to type it. And the way that we do that is to do this Hindley-Milner type system, which is a very popular type system in higher order functional languages. So I don't have much time to go into details, but I can show you what it looks like. So on the left, this is a type inference definition. And the interesting part is the let rule here. So in the let rule, whenever we see x equals E0 in E1, we need to do two things. One, we need to type E0 into a type tau. So that's the first thing. Second, we need to type E1 into the type tau prime. But we'll assign x a polymorphic type, a polytype. And the polytype is obtained by getting the type of E0, which is tau, and bind all the variables, the type variables that are generated during that process, you know, that typing process. So by typing E0, E0 may be polymorphic, so it may generate lots of free type variables. And we are going to bind all those variables in X and keep going, keep the typing. And note that this is a big step semantics, right? So it's a big style semantics. And we can do that in a small step way in K, but just, you know, it's a very straightforward correspondence. So whenever we see let X types to T, so we already know the type of T because we're doing a small step here. In E, we're going to do is we'll assign X to this polytype, T. And all the variables that are in T but not in the environment will be bound. And those are the variables that are generated during the type of T. So when we get T, T has some new fresh variables generated during its typing. That means that X is polymorphic only on those types variables, so we'll bound them. and then we start to type E. So it's pretty much, it's essentially the same thing, but we rewrite it in a small step semantics. And whenever we see a variable, which has a polytype, we instantiate it. So this rename k variable instantiate the bound variables, and then that can be, the equality constraint can be generated for those k variables. So yeah, so it's a very high level introduction, but that's also the only part we need to change. So the way that we type a lateral, everything else is still the same. So where's my mouse? Okay. So to sum up, we talk about the type.
But that being said, we typically caution users of K with respect to the use of meta features like this. You can do arbitrarily wrong and bad things using the meta level.
Right, because
and once you want to start extracting all the meta variables from a term and moving them around, then you have to know what you're doing. Otherwise, you can easily mess things up.
Yeah. So I think that this is just a nice way to do it, because K has this built-in unification module, but one can always just like create a new cell holding the most general unifiers and basically implementing the unification process in it. So that's also possible. But this is how we can use the internals built-in unification module in K. All right, so we talk about the type checkers, we talk about the type inferencers, so basically it's just use unification to solve equality type constraints. And we only discussed the environment-based definition, but substitution-based are also possible. And the exercise will be to defining the DHM type inference for fun, which is highly non-trivial, but the same principles in my idea will follow. So in summary, we talk about the vision of an ideal framework and the K framework, and we see how to use K to generate language tools. And we define the functional language fun, which lots of interesting features and its type systems. So I put some more references about the K, the overview K, and also its theory, matching logic. And we didn't have time to cover much verification, at all in this tutorial, but if you're interested, you can check out this OOPSA paper. So that's the end of my tutorial. Thank you so much for attending and your participation. So I can answer any questions. If I have any questions, please feel free to ask.
I do have a question. In the ... on this slide, the many things that are generated, can you generate some LaTeX corresponding to some of those rules?
Yes, yes.
Cool.
Actually, there is a LaTeX, so I didn't show it in the slides, but in an attribute, you can put a LaTeX, a LaTeX annotation, telling you how to generate those syntax in, using LaTeX constructs, so they look very beautiful. Yes.
And also the kernel C that you showed at the beginning, they generated from
the graphical notation.
Yeah. There are 3 or 4 different LaTeX shells, like this one. This is a tool. I think it's called KDoc. I'm not sure if it's updated anymore, but it's a tool KDoc that allows you to generate definitions like this. And also you can have Lambda. You can define arbitrary macros for productions in LaTeX.
Yes.
Okay, it's pretty open-ended. Everybody is free to and encouraged to contribute. The problem is that many capabilities evolved recently pretty fast, because there is also a company that is generating revenue using this toolkit around K, and they only update things that bring them immediate revenue, and sometimes things are out of sync and they need to be updated. But there used to be a callc backend as well to K that to generate callc definitions, not only LaTeX definitions. like this. But one thing which is different in K from conventional small step or big step SOS is that it has this particular style of writing semantics, and no matter how you generate your LaTeX, it's not going to look like small step SOS or big step SOS. So that's why we didn't even try to anymore. So we generate rules like this.
Yeah.
Properly.
Okay, so if any questions? Yes.
Just wondering about syntax highlighting and generating syntax highlighters and other things that you might use in an IDE, for example.
That would be beautiful. That would be beautiful. We tried to use spoofwax at some moment, but again, as usual, things were not maintained, updated. So I think many people just use Emacs these days with K definitions, but it would be really nice to have an IDE.
Yeah.
There was a syntax highlighter in Emacs and one in VIM, I think, but the problem is that there is this two level of parsing, right? So you like to assign colors to productions in your syntax definition, and then you like your IDE to use it, like in spoofwax, which is really nice. But it's not easy to implement like an Emacs shell to do that.
So hang on, I guess there's sort of two levels of syntax highlighting, like syntax highlighting the actual K code, but then for the language you generate, syntax highlighting for the language that you've defined is more what I mean.
Yes, that's true. Also, now we define the syntax of K as a syntax. As I mentioned, we define K in K, and then we define the syntax. We want to allow people to change the syntax of K, because sometimes the syntax of K collides with the syntax of your programming language. So we actually literally have the syntax of K in a file in K, the same way as any other syntax of any other language. And we have these attributes with colors, that allow you to associate colors to formatting to productions. So in that light, they become the same. But you are right. There are two different levels of coloring and parsing.
Okay, so
it's not trivial at all. I think Elko knows it well. He can tell us how hard this is. So we actually gave up.
Are there?
Mm-hmm.
Oh, there you go.
Yeah. Any more questions?
Yes. I was just wondering, you've mentioned the verification side. So I was just wondering, what are some of the kind of areas in which K is kind of strong, or limitations of the verification that you've encountered?
So on the verification, I think we are pretty, so we have a K prover, which can prove any reachability rules. So all these whole triples, style of program correctness, functional correctness, so we can do that in K. Of course, the users need to give, for example, if there is a looping loops, you will need to provide invariant conditions, just like the other verification tools. But apart from that, I think that tool is pretty complete in terms of formal verification. We are currently developing some more formal analysis tools like the bounded model checkers, but that's still in the development.
Okay, interesting. Thanks. Yeah.
So we do not do any inference, any invariant inference currently. So if you have loops in your program, you're supposed to provide lemmas, which are other rules, right? So we specify everything with rules, right? So Hort triple for us is also a rule, where you have the precondition and the code all bundled together in a symbolic configuration. Rewrites to the postcondition and the empty cell of code as the target configuration. And then there is this matching logic proof system that allows you to prove rules from other rules. So the original semantics is like a set of axioms or a theory, and then using the proof system, we can derive other properties, including such reachability claims about programs. But if you have loops, you will have to provide lemmas, which are reachability claims capturing the behaviors of these loops, which is the equivalent of invariants in Hoare logic style verification. And actually, there is even an automated procedure to take Hoare logic verification, Hoare logic proofs into reachability logic proofs. So if you want to use an off-the-shelf program verifier like Boogie for a particular language, then you can generate from that all the artifacts that you need to reconstruct the proof based on the actual operational semantics of the programming language in K. And in fact, this is the main source of revenue in my company, in runtime verification. If you go to runtimeverification.com, we do this for smart contracts, right? So there is a semantics of the Ethereum virtual machine in K, and the main service that the company offers is formal verification of smart contracts. And it's all about doing what I said previously, but for a particular language, the Ethereum virtual machine, EVM.
Thanks. Yeah. So does, you mentioned it can link to Boogie. And so imagine, so one, does it link to other SMT solvers that I guess Boogie links to? And also, you mentioned the COC backend. Is that like close, or is that working, or is it out of date?
I think it is out of
Okay.
I saw Stefan Ciobucă here for a while. He disappeared. He worked on that for a while, but I don't think it's updated.
Okay. Cool. Yeah, it would be nice.
I agree. Yes.
I have two questions as a newcomer. Is that fine?
Yes, of course.
Before my questions, I want to thank Grigor Roche and Xiaohong for this enlightening course. We had fun. Dossier, I born in 2000, and I feel very lucky to know that this tool is emerged my age of work. For first question, I want to ask whether it is sane and trivial to define languages that will mainly run on GPUs and do heterogeneous, loosely synchronized computation, and how bad the runtime of K framework can get while doing such verification-related computation.
I'm not sure I heard well the question. Maybe Xiaohong, you heard well on your side?
Yeah, can you repeat the first question?
It's one question. So is it trivial to define languages that will run on heterogeneous, loosely synchronized computation, and how bad the runtime of K framework can get while verifying such computation? Like GPUs.
We have not defined those, right?
Yeah, we don't have that experience. I don't know, actually.
Okay, then I will ask my second question. I found K-framework's documentation a bit less accessible. For example, some modules have many useful constructs in them, but you have to explore the source to find out. Will there be an effort to improve this, and will it be possible to contribute?
The K documentation, right?
Yeah.
So I think we kind of, because K is still a moving target, so we don't really have a very well-maintained one, like a well documentation for K. So I would say the best way to learn K is to go to the tutorial. So if you go to GitHub and K folder, there's a K tutorial in it, and it's pretty comprehensive. It covers all the basic features you know about K. And in my opinion, so the first few lectures, 2 lectures, basically told you, will teach you 80% of the K features you ever need in defining your programming language. So I highly recommend it. If you want to learn K, just go to the K tutorial.
And also ask questions on Stack Overflow. I think there's a K framework tag now there, and also on Slack. There are lots of questions being asked and answered by users.
Yeah.
And the task of writing a reference manual has been taken by people at runtime verification at the company, which means that hopefully it will happen soon. In the past, it was the job of my lab at university, and nothing happens there except papers.
I see. That's great to hear.
Sorry, Xiaohong, you know it, right?
Yeah.
I don't know how to convince students to write a reference manual. I just don't. I tried. They don't.
On your first question about the GPU, I think so. Yeah, we don't have anything defined, anything like that defined, but we do have the x86 semantics, and as far as I know, it is a very complex semantics with lots of rules and cells. So, but I don't know much about the performance. But I mean, I would just say that there might be something similar that we have defined in the x86 semantics defined in K. So it's definitely doable.
Mm-hmm. Yes, I can see how that generalizes. Thanks a lot.
Yeah. All right. So any more questions? So if not, thank you all again for your attendance, and be very happy. And just if you have any questions after this talk, just send me an email. You can,
Vadim has another question. Vadim, go ahead.
Oh yeah, I see them. Yeah, go ahead.
Please.
No, I was applauding. It was
it's
good to have this. Yeah.
Okay. Yeah. Thank you.
Thank you very much for the questions. Great questions, guys. And feel free to contact us anytime.
Yes.
We'd be glad to stay in touch.
Yes.